So what is, how do you solve for this W? Well,
So what is, how do you solve for this W? Well, this model,
let's go ahead and
do
the
write down the model. So this model is sometimes called as logistic regression. You must be careful. Why is it with this name? Though it's called logistic regression. So what is, how do you solve for this W? Well, this model, let's go ahead and do the write down the model. So this model is sometimes called as logistic regression. You must be careful. Why is it with this name? Though it's called logistic regression, it's still a classification model. The name logistic comes from the fact that, of course, we are using the logistic function of the sigmoid function. It's called regression because these probabilities internally depend on a W transpose X score, which is a real number, and so this is sometimes called as logistic regression. But the real use is that it's going to be used for classification purpose. Okay. You must be careful. Why is it with this name? Though it's called logistic regression, it's still a classification model. The name logistic comes from the fact that, of course, we are using the logistic function of the sigmoid function. It's called regression because these probabilities internally depend on a W transpose X score, which is a real number, and so this is sometimes called as logistic regression. But the real use is that it's going to be used for classification purpose. Okay. So of course we have this, right? So probability of y equals 1 given x is now given by, well, the generator of the labels has some W which we don't know, right? So and with respect to that W, the probability that y equals 1 is 1 by 1 plus e to the minus W transpose x, right? So this is what we were calling as Z before, but now there is some W such that this is the probability that y equals 1 given x. Now of course we have a data set, right? So what we probability that of course we are using the logistic function of the sigmoid function. It's called regression because these probabilities internally depend on Hello everyone, welcome back. So far we've looked at the perceptron algorithm for binary classification, and we have argued that the perceptron algorithm will in fact find a linear classifier if the data that is given is linearly separable. We also argued that the perceptron algorithm's number of mistakes, right? So perceptron, the number of mistakes that perceptron makes depends on, is at most, right? So let me put this way: perceptron mistakes is less than or equal to r squared by gamma squared, where r is the radius of the data points and gamma is what what we were calling as margin. That is when the data set is linearly separable. Makes depends on is at most, right? So let me put perceptron algorithm. Hello everyone, welcome back. So far we have looked at the perceptron algorithm for binary classification, and we have argued that the perceptron algorithm will in fact find a linear classifier if the data that is given is linearly separable. We also argued that the perceptron algorithm's number of mistakes, right? So perceptron, the number of mistakes that perceptron makes depends on is at most, right? So let me put it this way: perceptron mistakes is less than or equal to r squared by gamma squared, where r is the radius of the data points and gamma is what we were calling as margin. That is when the data set is linear. Linearly separable with gamma margin, then what we are able to argue is that perceptron's number of mistakes is a finite quantity. Then margin. That is when the data set is linearly separable with gamma margin, then what we are able to argue is that perceptron's number of mistakes is a finite quantity. It's bounded by r squared by gamma squared. Now, this needs a very closer look. What does it mean to say the margin is gamma and so on? And that needs a longer discussion, and the algorithms that will come out of it will need a longer discussion. So what we're going to do is we're going to do this afresh in the coming week. But for now, we'll part the idea of perceptron that here is an algorithm, and we know that algorithm converges when the data is linearly separable, and we know the number of mistakes that it makes is bounded by the radius squared divided by the margin squared. This is the understanding that we have right now. We'll come back and revisit this idea of margin a little later, perhaps the next week, where we will have a longer discussion about this and then see what kind of algorithms that this discussion will inspire. But for today, what we wanted to do is to see what is the assumption that perceptron makes, and can we rethink this assumption in a slightly different way. So if you remember, the assumption that perceptron makes is a linear separability assumption, right? So but if you want to write that in a probabilistic way, then one way to say that is that probability of y equals 1 given x, this value is just 1. That is certainty. You will predict 1 if w transpose x is greater than or equal to 0, and this probability is 0 otherwise, right? So that is, there is a probability, but then it is not really, a non-trivial probability, right? So which means that this is essentially, we have argued that this is essentially saying that the data set is linearly separable with the separator given by the plane perpendicular to w. Now, because of the strict assumption about these probabilities being just 1 or 0, perceptron is unable to model data sets like this, right? So if you have let's say plus minus 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 minus, unable to model data sets like this, right? So if you have let's say plus minus 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 minus, let me put this in the black color. Now, if you have a minus here and if you have a plus here, we know that this data set is not allowed under the perceptron model. Why? Because when I'm trying to label this, when there is a labeler who's giving me labels for this data points, well, that is going to depend on some w, maybe the w is here, and that w says that, well, everybody on one side is plus, the other side is minus. But then if the labeler had used this w, then that labeler would have labeled this point as why? Because when I'm trying to label this, when there is a labeler who's giving me labels for this data points, well, that is going to depend on some w, maybe the w is here, and that w says that, well, everybody on one side is plus and the other side is minus. But then if the labeler had used this w, then that labeler would have labeled this point as plus and this point as minus. But because we're seeing the other way in the data set, this data set could not have been generated according to the perceptron assumption, which is this. And if you look closely at this assumption, the main culprit is the fact that we are assuming that the probabilities are exactly 1 and 0. So can we somehow relax this assumption, right? So that's the question we're going to ask now, and then we'll see that what kind of algorithms that will lead us to. So the question we're going to ask is, can we model the probabilities differently? What do I mean by differently? Well, let's see what does differently mean. There are several ways you can model it, and here is one natural way that you might want to do this, right? So we can start with a simple model, right? So start with a simple model. Well, what is a simple model? A simple linear model. Simple models are typically linear. What does that mean? That means that you have some z, so which is like a score for a data point with respect to some w, right? So x is again your feature, right? So this is your feature vector. X is in RD as usual, and then there is some w. But now if I do w transpose x, and if I'm looking at that value, now that value is like a score that w gives for this data point x, right? So in pictures it would mean something like this. You have this two-dimensional plane. Let's say this is our usual w that we typically take as an example. Now this line is just a set of all x such that w transpose x equals 0. That is the score that w gives to all the x on this line is just 0. Now, one might ask where are the set of points for which the score is 1, right? So now if you think about that, so that's going to be somewhere here, right? So that's just going to be a line which is parallel 1 unit with respect to w. So this is just the set of all x such that w transpose x equals 1. Now, similarly, where are the set of points for which the score is minus 1? Remember, the score is just a dot product, the way we are thinking of it. So the score, this is set of all x such that w transpose x equal to minus 1. Well, if the score is negative, then we are somehow saying that the data point is highly probable to be labeled minus 1. If the score is positive, then the data point is probable to be labeled as positive. But now there is a difference that we want to incorporate in our model between data points that are here and perhaps a data point which is maybe somewhere here, right? So maybe this is a line which also has a data point. Now this data point, is the set of all x such that let's say w transpose x is 100. Right, so if you move 100 units away in the parallel in the direction of the plane that separates, that is perpendicular to w. Now, if I'm generating these two, if I'm generating labels for these 2 points, let's say somebody gave me these labels, and now I have to give you, let's say somebody gave me these points, right? So let's call this x1 and let this point as x2, and now I have to give you labels for these points. Well, I want to somehow associate a probability with these labels, right? So this label can be either 1 or minus 1. Earlier we were saying that this probability that the label is 1 if it falls on one side of w, which means that both these points will get labeled as 1 with probability 1 for this w, right? So whereas there might be 2 other points on this side, maybe x3 and x4, maybe x3 is here, and there is a corresponding, maybe there is some x4 out here, which I'm going to put it here. So this is the set of all x such that w transpose x equal to minus 150, let's say, right? So this is parallel on this side, 150 units. So now these labels, right? They want to now, one might ask where are the set of points for which the score is 1, right? So now if you think about that, so that's going to be somewhere here, right? So that's just going to be a line which is parallel 1 unit with respect to w. So this is just the set of all x such that w transpose x equals 1. Now similarly, where are the set of points for which the score is minus 1? Remember, the score is just a dot product, the way we are thinking of it. So the score could be minus 1, and that minus 1 could be somewhere here, right? So this is set of all x such that w transpose x equal to minus 1. Well, if the score is negative, then we are somehow saying that the data point is highly probable to be labeled minus 1. If the score is positive, then the data point is probable to be labeled as positive. But now there is a difference that we want to incorporate in our model between data points that are here and perhaps a data point which is maybe somewhere here, right? So maybe this is a line which also has a data point. Now this data point, is the set of all x such that let's say w transpose x is 100. Right, so if you move 100 units away in the parallel in the direction of the plane that separates, that's perpendicular to w. Now, if I'm generating these two, if I'm generating labels for these 2 points, let's say somebody gave me these labels, and now I have to give you, let's say somebody gave me these points, right? So let's call this x1 and let this point as x2, and now I have to give you labels for these points. Well, I want to somehow associate a probability with these labels, right? So this label can be either 1 or minus 1. Earlier we were saying that this probability that the label is 1 if it falls on one side of w, which means that both these points will get labeled as 1 with probability 1 for this w, right? So whereas there may be 2 other points on this side, maybe x3 and x4, maybe x3 is here, and there is a corresponding, maybe there is some x4 out here, which I'm going to put it here. So this is the setup, right? So this is parallel on this side, 150 units. So now I have to label x1, x2, x3, and x4, right? So I have to give you labels. Earlier, our assumption would say that I will just give you labels 1 for x1 and x2 and minus 1 for x3 and x4, and that allowed only linearly separable data sets. Now what I'm going to say now is that I'm going to allow for labels to be both plus 1 and minus 1 for all points. But what will decide these labels? Well, there should be some probability for the label being plus 1, and there is some probability for the label being minus 1 for each of these points. Now what will decide this probability? That probability will be decided by how high or low the score associated with this point is. Which means that if I take a point like x1, which is here, versus x2, which is here, now if you ask the question, well, which one should get a higher probability of being assigned to class 1? Well, for this w, this x2 is much far away from the separator, right? So which means that you are somehow more confident that this point has to be labeled plus 1 as opposed to x1, which is close to the boundary, which means that the probability that it should be labeled plus 1 should be lesser than the probability that x2 is labeled plus 1, right? So which means that as I move in this direction, my probability that the point is labeled 1 should increase, whereas as I move in this direction, the probability that a point labeled -1 should increase, right? So still, remember, every point gets a non-zero probability of being +1 or -1, but then the chance that it becomes -1 somewhere here, and the end of, if you move further away in this direction, goes down, right? So somehow we need to capture this intuition using the score, right? So, but remember, the score itself is not a probability, right? So the score z is in -infinity to infinity, right? So it's a real number. So we have to convert the score somehow into a probability, and the question is, how can we do that, right? So what do we want here? We want the following: larger the value of z, larger the score, which is z, w transpose x, more the probability of being 1 plus 1, right? So because a large positive number should get a large probability of being +1, a large negative number should get a large probability of being -1, which means a small probability of getting +1, right? So we can just then decide the probability of being 1 using the score. But how to decide, right? So how can we convert the score into a probability? Well, what we want about the score, right? The first question is, what happens if we find a point which lies on the separator, right? So it's exactly lying on the separator, which means that we are not really sure if there's going to be +1 or -1, so we can give equal probabilities for them, right? So which means that we want some function g such that which takes the score as input and outputs as probability, but this g of z should be 0.5 if z equals 0. Right? So whenever the score is 0, which means that the point lies exactly on the separator, we want the probability of that being labeled +1 as 0.5 and -1 also as 0.5. Now we want g of z, the probability of the point being labeled 1 to converge to 1 as z becomes larger and larger, which means that as z becomes infinity. Similarly, we want g of z to converge to 0 as z becomes -infinity. The smaller and smaller the score is, the chance that it being labeled as +1 should z becomes larger and larger, which means that as z becomes infinity. Similarly, we want g of z to converge to 0 as z becomes -infinity. The smaller and smaller the score is, the chance that it being labeled as +1 should go to closer and closer to 0. So any g that satisfies these three properties is a reasonable g to use, right? So this g is sometimes in literature is called as a link function because it links scores to real numbers to probabilities. There are several link functions that you might encounter in practice, but one of the most popular link functions, one popular choice for link function is the following. So g of z equals 1 divided by 1 plus e to the minus z, right? So this function is called sometimes as the sigmoid function or logistic function, and I'll plot this function and show you how this looks like, right? So this function will look like the following.
So nothing special is going on here, right? Just we are incorporating the outliers, and it's kind of encoding in a mathematical way. Like if the data points are close to the margin, then we will have less certainty about whether it will lie to the positive side or the negative side. And if it happens that it is far away from the boundary, then we will be quite confident about it there, right? So that is being encoded here with the help of this z value and this linking. So
So this is going to take a value of 0.5. Maybe I'll draw. So these are probabilities, so it's never going to take a negative value. As you can see, right? So it's e power something, so it's always going to be positive, and it's 1 divided by 1 plus e power something will always be a positive quantity. Right? So it will take a value of 0.5 when z is 0. So this is z. This is g of z equals 1 by 1 plus e power minus z. And here is 1. And let us put a virtual line here.
just we need to substitute here the value of z equals to 0. So this will be 1, and 1 by 2 is like 0.5. So we are getting 0.5 here.
Now, if you look at this, so if you plot this function, it's going to look like this, right? So it will get, so this should not touch here, right? So as z goes larger and larger, right? So this is 0, this is infinity, this is minus infinity. As z grows larger and larger, the sigmoid function's probability that it gives that z the point is labeled +1 goes closer and closer to 1, and as z becomes closer and closer to minus infinity, the probability becomes closer and closer to 0. It's called the sigmoid because this looks like an S, and S stands for sum, and sigma is the the Greek symbol for sum, and so it's called a sigmoid function. Okay, so this is
Yeah, so idea is basically that we are just mapping this range of minus infinity to infinity to, like, in the probability we know that the probability mass function should lie between 0 and 1. So we are just mapping the score of minus infinity to infinity within a range of 0 to 1. Nothing fancy right here. Just you may think like this function is very unreal to see at the first glance, but it is very simple, right? We just have to put this z on z here. That's all. So what we have done till now is, like, we have defined the probability like probability for a given point using this z. No, not the probability but the score, right? So we have encoded the score using this z variable, and after that we are getting the score. We are just simply taking the score in the z function to map it between 0 to 1, and we we could give a threshold like say 0.75. So after above 0.75 we will mark the data point as level 1, or below that it will be marked as -1, right? Means what I mean to say is that we will
This is a reasonable
we will just give a threshold here, like a parallel line to the x-axis, and below that we could like our logic would be to map all the points that such that their probability lies below that threshold as -1, and above that as the +1.
choice, and we'll see why this is a reasonable choice.
later on because it makes certain math easier, as we'll see in a minute. But now this is all we are saying right now is that we have a model as to how the data could have been labeled. Now let's ask the question, well, can I, under this model, do I allow a data set like this, right? So this is what we were not allowing earlier. This was okay. This data set is still okay even with perceptron, but then this data set was not okay, right? So if the moment I put up minus and plus on the opposite side of the one fixed w, then it's not okay. Now is this data set allowed according to this model, right? So this model is
So in the perceptron model, like the assumption is like we should have a strict linear separator, right? And if there exists even a single point that does not follow the rule of linear separability, then the perceptron algorithm will not converge. But we are kind of relaxing the assumption made in the perceptron algorithm. So I hope you are able to recall what's the assumption right there. The assumption was just linear separable condition along with the gamma margin, right? I will discuss that in further in future videos. Okay.
sometimes called as the sigmoid model or the logistic model. Do we allow this data set? Yes, we allow this data set because now there might be some W, right? So such that, so these points, so for every point in my data set, before deciding the label, this is what should have happened, right? So for example, let's take this point. Why was this label +1? Why was this label positive? Because this point falls with respect to this W on this line, and this line is just the set of all x such that, let's say, W transpose x is 1, which means
Okay, let's try to figure out why we have a positive region in this side of the linear separator and a negative region in this side of the linear separator, right? So let's try to figure out why that's the case. Take this picture. See. So let's try to understand here. So let's say we have a axis like this, and then we have a linear separator like, then we have a linear separator like this, right? So, and let's say the W is like this, and let's consider a point here. Let's consider a point. Let's consider a point here, right? So why I have marked it as plus? We will try to figure out why I have marked it as +1. Right? So already in the earlier lectures, like maybe in week 5 or 6, sir has discussed why this region is marked as positive and this region is marked as negative, and all the data points that should lie that will lie in this line or the linear separator. So in 2D this line this is a line, right? In 3D it could be a plane, and in 4D and above that it will become a hyperplane. So all the points that are lying in this hyperplane will have a dot product of 0. Why? Could you think of why? So see, here we have the W vector, right? Here we have the W vector, and let's consider a point here. So if we make a vector, so this vector is just coinciding with the line, and in my earlier video I have discussed that if there is an hyperplane and then means we have the normal vector like this. So this is my so this is the hyperplane and this is the normal vector. So the angle between this should be 90 degrees. And from the definition of dot product, we know that it is like and from the definition of dot product, we know that the dot product of two vector is given as like uh, this is the actual vector. So it is given like a mod of x mod of w times cos of the angle between these two vectors, right? So as the angle is like 90, so this and the dot product will turn out to be 0, right? Because cos 90 is 0, so it 0 then will be product with the magnitude nearly giving result of 0. So all the points, any point which lies on this linear separator is will have a vector 0, and any point that lie in this region will form an acute angle, right? Will form an acute angle. And since the see what I am saying, like guys are doing this concept very well. So x dot y is like x vector mod of x mod of w times cos theta, right? So uh, these two things are positive, so they will not contribute in the sign. The only thing which could contribute in the sign is the cos theta, right? So the cos theta will determine the sign. So in this region, in this subspace, we could say that this is a half subspace, right? Because the whole region is divided into two equal halves. So this is a half subspace. So any data point lying in this region will form a acute angle with this w, and thus the dot product will be positive, right? And that you could think, I mean, you can easily figure out that the dot product will become the dot product will come out from very minute positive quantity to a huge quantity, because this two will scale, right? So if it's perfectly line up, let's say plus 1, cos theta value is plus 1, right? Then this the scale of these two will determine how big is the dot product will be. So it will go to plus infinity in the positive case, as in the negative case it could go up to minus infinity. So that's the concept. Okay.
That I have actually tossed a coin whose probability of coming up heads is 1 by 1 plus e power minus 1, which is 1 by 1 plus 1 over e, which is e by e plus 1, right? So this is the chance with which this point gets labeled as plus 1. So which means that I've tossed a coin, and that coin whose probability, whose bias, right? So for probability of falling heads is e by e plus 1, and that coin actually fell heads, and so this point was labeled as plus 1. That's the assumption we are making. Now, why was this point labeled minus 1? Well, which means that I have actually tossed this. So the moment I put up minus and plus on the opposite side of the one fixed w, then it's not okay. Now, is this data set allowed according to this model, right? So this model is sometimes called as the sigmoid model or the logistic model. Do we allow this data set? Yes, we allow this data set because now there might be some w, right? So such that so these points, so for every point in my data set, before deciding the label, this is what should have happened, right? So for example, let's take this point. Why was this labeled +1? Why is this labeled positive? Because this point falls with respect to this W on this line. And this line is just the set of all x such that, let's say, W transpose x is 1, which means that I have actually tossed a coin whose probability of coming up heads is 1 by 1 plus e power minus 1, which is 1 by 1 plus 1 over e, which is e by e plus 1, right? So this is the chance with which this point gets labeled as +1. So which means that I've tossed a coin, and that coin whose probability, whose bias, right? So probability of falling heads is e by e plus 1, and that coin actually fell e whose 1. Allow this data set, because now there might be some W, right? So such that, so these points, so for every point in my data set, before deciding the label, this is what should have happened, right? So for example, let's take this point. Why was this labeled +1? Why is this labeled positive? Because this point falls with respect to this W on this line, and this line is just a set of all x such that, let's say, W transpose x is 1, which means that I have actually tossed a coin whose probability of coming up heads is 1 by 1 plus e power minus 1, which is 1 by 1 plus 1 over e, which is e by e plus 1, right? So this is the chance with
Sir is assuming that this line have a score, that is, this is nothing but z value, right? So this line have a z value of 1. So we are just substituting the value of the z here 1. That's all.
which this point gets labeled as +1. So which means that I've tossed a coin, and that coin whose probability, whose bias, right? So probability of falling heads is e by e plus 1, and that coin actually fell heads, and so this point was labeled as +1. That's the assumption we are making. Now, why was this point labeled -1? Well, now again you do the same process, right? So this point is in the set of all x such that W transpose x equal to, maybe 10. Now in this case, well, again there is a chance that this guy gets a positive label, and that chance is in fact greater than the chance that this guy gets a positive label. In fact, that will be 1 by 1 plus e power minus 10, right? So which will be e power 10 by e power 10 plus 1. Right, so now I have tossed a coin with this probability, and that coin fell tails, right? So I have labeled this point as -1. It is not a zero probability that it will show up as -1, right? So though it's a minuscule probability, in that if you do an experiment where you're assuming that the labels were generated according to this coin tosses, where the coin's bias depends on how far away from the separator this point is, in the sense of the score that we have defined earlier. So then every point could get some chance of being +1 or -1, right? So now we're assuming that these points have been labeled because they fell heads or tails according to their labels, right? Now one might ask the question, well, the moment I say that, well, every point could have been +1 or -1 depending on how far away it is from the separator that defines W. Now one can say that, well, why only this W, right? So I could have had a completely different W. Maybe I am looking at a different W here, right? So now this is W dash. This W dash separates like this. Now I can still say, right? So even with this W dash, this data set is still possible. Why? Because this data set, now the same point here now would have a different line, right? So a different score with respect to this new W that I've defined here, right? So I mean, I should draw the W carefully so that it looks perpendicular, but yeah. Right, so this with respect to this W, again I get a probability that each point is +1 or -1, so I would have tossed a coin and I've gotten this labels, right? So basically then that means that you have seen a data set with certain labels. Now every W has a probability of generating these labels, right? So now every W could be is a contender for being the W that actually generated the labels, which means then now our problem becomes as to, because every W is a possible W, I need to pick one W which I think would be the best W for this data set. So now I can pose this as a problem where I'm trying to find that W which has the highest chance of having generated this data, which is simply a maximum likelihood estimation problem, because for every W there is a probability that it generates the data that I see, the labels that I see. So which W has the highest probability of generating this data? That's a typical estimation problem that we know how to solve, right? So let's go ahead and see.
Yeah. Okay. Many things have been covered right here. So let's start from quite a little back, right? So in the perceptron, we have kind of given a very strict restriction that, okay, I am not going to allow any outliers. I am not going to allow any outliers, right? But here in this model, we are saying that, okay, if some outliers are coming right there, then our model is capable to handle it. And how we are going to model it is like, we have maintained a score z. We are calling it as a variable z, So z variable is nothing but a w transpose x, right? And the value of the z could vary from minus infinity to plus infinity. And then we will go ahead and find this function g of z, right? So which will map this minus infinity to any value that will come out from the z to a probability score, right? But the problem in that but the problem is like okay, so every data point will be assigned a probability of getting positive or being negative. But now, even if let's say there is a coin and the probability of coin is like, say it will throw heads point 99 0.999, like have a probability of 0.99, like means what I mean to say is that, let's suppose there is a coin, and if we are tossing the coin, the chances of appearing head is 0.99. Even in that case, there is a means there is a chance of coming a tail, right? Even though the chance is very less, but there is a chance a tail could appear, right? So the same thing is being encoded here. So if we allow that kind of model, then definitely there could be different w's which could generate the data set, right? Like this is also this w is also the contender, and this w is also a possible contender. So we have, like, say again, we have 4 to 5 w's which could compete and try to generate the data. Then the question arises, like, which w we will going to pick, right? So it turns out that it is nothing special and we are doing nothing new right here. It's just simply a estimation problem. We know the model, what model we are using. We know what's the data set, and we know what's the parameter is involved. We just need to get the right value of the parameter, and that's the typical estimation problem, right?
The labels that I see. So which W has the highest probability of generating this data? That's a typical estimation problem that we know how to solve, right? So let's go ahead and do that.
Hello.
So what is, how do you solve for this W? Well, this model, let's go ahead and do the write down the model. So this model is sometimes called as logistic regression. So what is, how do you solve for this W? Well, this model, let's go ahead and do the write down the model. So this model is sometimes called as logistic regression. You must be careful. Why is it with this name? Though it's called logistic regression, it's still a classification model. The name logistic comes from the fact that, of course, we are using the logistic function or the sigmoid function. I call regression because these probabilities internally depend on a W transpose X score, which is a real number, and so this is sometimes called using the logistic function or the sigmoid function. I call regression because these probabilities internally depend on a W. Logistic comes from the fact that, of course, we are using the logistic function or the sigmoid function. I call regression because these probabilities internally depend on a W transpose X score, which is a real number, and so this is sometimes called as logistic regression, but the real use is that it's going to be used for classification purpose. Okay, so of course we have this, right? So probability of y equals 1 given x is now given by, well, the generator of the labels has some w which we don't know, right? So and with respect to that w, the probability that y equals 1 is 1 by 1 plus e to the minus w transpose x, right? So this is what we were calling as z before, but now there is some w such that this is the probability that y equals 1 given x. Now of course we have a data set, right? So what we see is this data set, which is x1 y1 dot x and yn. Now question is how to find w, right? So we are assuming a model which depends on a parameter w. We have a data, so we can estimate w. And what is how to find w? Model is sometimes called as logistic regression. You must be careful. Why is it with this name? Though it's called logistic regression, it's still a classification.
So logistic regression is because there is like the sigmoid function is used here in order to map the z to the probability, and the regression is because like we are finding the value of z. That's why, and the value of z is like a continuous between minus infinity to infinity. That is z. The value of z is real, right? So for a for a real valued output, the term regression is generally used. So that's why it is named as logistic regression.
Model. The name logistic comes from the fact that, of course, we are using the logistic function or the sigmoid function. I call regression because these probabilities internally depend on a W transpose X score, which is a real number, and so this is sometimes called as logistic regression. But the real use is that it's going to be used for classification purpose. Okay, so of course we have this, right? So probability of y equals 1 given x is now given by, well, the generator of the labels has some W which we don't know, right? So and with respect to that W, the probability that y equals 1 is 1 by 1 plus e to the minus W transpose X, right? So this is what we were calling as Z before, but now there is some W such that this is the probability that y equals 1 given X. Now of course we have a data set, right? So what we see is this data set, which is x1 y1 dot x and yn. Now question is how to find W, right? So we are assuming a model which depends on a parameter W. We have a data, so we can estimate W. And what is how to find W? Well, we know one powerful method to do this, which is the method of maximum likelihood. Let's try that, right? So which means if I have to do maximum likelihood, by now,
Yeah. So even though we have used maximum likelihood in kind of different places, like in statistics 2 we have used, statistics 1 we have used maximum likelihood, and probably in the MLF we have already used maximum likelihood, and even in the unsupervised learning part and in the supervised learning paradigm we already have used maximum likelihood like a couple of times, right? So even if you have certain confusion, so the idea is like uh, let me just give you a small clue. Yeah. So idea is like we have a data set. We have a data set. Yeah, so x1 is there, y1 is there, all the way up to xn, yn is there, right? So from x1 y1 to xn and yn, and our goal is to find a group W. And we typically denote it using like y hat, right? Sorry, w hat. So what likelihood is like, it is simply the product of the probability of is simply the product of probability of xi given w, and I will go from 1 to n, right? That is, we are kind of maximizing the value, and that value is simply the product of the probability. And this let me reiterate. Okay, so first of all, let's try to figure out what this is saying. So let's pick a point. Let's say xk we have picked, right? So what we will go ahead and do is, we will try to figure out, okay, what's the probability of that we will get a data point xk given that we have this w is still unknown. But like, we how we try to estimate a certain value, then we used to denote with x, right? So the x is unknown, but it is just there like a symbol. The same concept is used here. W is unknown and it is just like a symbol, so the our answer will come in form of w, right? So this whole function will come in a form of w. So that whole thing we will call as likelihood. So it is called a likelihood function. So there is nothing so mysterious or to be tense. You just need to remember this expression, that we are just finding the probability of the data point given that w, and the product of this data point is just the likelihood. Simple concept.
We should know how to do maximum likelihood. Write down the function, which means write down the likelihood function. The likelihood is a function of the parameter that I'm trying to estimate, in this case w, and the data.
Yeah, so you can think, means it is obvious, like, uh, the value of the function, that is the likelihood, will depend upon what? Will depend upon these two things, right? This is a this is a part of data set, and this is the parameter. So that's why sir is like, it is a function of w and the data set itself.
So what is this going to be? We are going to assume that somebody gave the features, and then the probability is only with respect to the labels, and each label is generated independently of the other labels. That's a usual assumption.
So there is an inherent assumptions. There is an inherent assumption, that is the data point, that is the generation of each data point should be independent of each other. That's why we are able to get this product, right? If 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 these 2 points are not independent, then there will be a kind of complex relationship. So basically, it is what actually this is the probability of finding x1, x2, x3, xn, even w. And there is an assumption of independence, right? So the independence assumptions will lead to this thing, like probability of x1 given w times probability of x2 given w, and so on. That's why, since it is multiplied, so there here we have the product name.
So which means that I can write this as a product of I equals 1 to n data points, and that is n. So now let's just call this g of w transpose x, so that it's easier to write g here. So this is g. So for the first data point, if it is plus 1, it happened with the probability g of w transpose xi. If it is minus 1, it happened with the probability g of 1 minus g of w transpose x. So for g of w transpose x, so that it's easier to write g here. So this is so labels, and each label is generated independently of the other labels. That's a usual assumption. So which means that I can write this as a product of I equals 1 to n data points. That's why this is n. So now let's just call this g of w transpose x, so that it's easier to write g here. So this is g. So for the first data point, if it is plus 1, it happened with the probability g of w transpose xi. If it is minus 1, it happened with the probability g of 1 minus g of w transpose xi. If you remember the Bernoulli maximum likelihood function that we wrote down, like it's exactly similar, right? So just that there it was just a p. Now that p has a functional form which is g of w transpose x. So power yi into 1 minus g of w transpose xi power 1 minus yi, right? So yi, of course, in this case, we are assuming yi is 0 or 1, right? Okay, so of course g has this functional form, but right. Okay, so of course g has this functional form, but before we plug in g's functional form, let's take the logarithm of this. You look at the log of the likelihood of w with respect to the data. That is just going to be sum over I is 1 to n yi log
Okay, so I have a doubt, like why we are using the product of y hat, right? This
g of w.
g of w transpose xi is nothing but y hat. That is our prediction for a given data set. Like I need to see like why, yeah, though it is kind of intuitive, but I am not like crystal clear that why we are just maximizing y hat.
W transpose xi plus 1 minus yi log 1 minus g of w transpose xi, which is simplified as, now let me plug in g. G is 1 plus 1 by 1 plus e power minus w transpose xi plus 1 minus yi log, well, 1 minus this, this is the probability of 0 happening, which is 1 minus 1 plus e power minus w transpose xi, which is just going to be e power minus w transpose xi by 1 plus e power minus w transpose xi. Now you can see that this functional form of using the e power things in the probability is actually helping, because when you do the log likelihood, the logs and the some few of those cancel out, right? So this can be written as,
Yeah, so definitely it's a probability, means property of log, that the log breaks the multiplication, means so anything which is under the log and they are in the multiplicative form, so what log will do is, let me, I, I know you guys know this very well, right? Like if there is a log of ab, then it is like log of a plus log of b. Yeah, so this is nothing like the that thing, like p of g pi of I equals to 1 to n, and there is w transpose xi raised to the power yi blah 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 and all the things. So as they are in the product, so after taking the logarithm, that this each and every element comes in the summation form. That's all, nothing new.
as I equals 1 to n, the way I'm going to write this is, so there is 1 minus yi. The log of e power minus w transpose xi will become 1 minus yi. The log and the e in the numerator will cancel, will be minus w transpose xi. There is a log of e power minus. This is logs and the e power things in the probabilities actually.
Yeah, so here we need kind of more explanation. Like you just need to expand this once again. What you should do is like you should further divide this in this form. Like log of a divided by b is like log of a minus log of b, and this thing will be multiplied with 1 minus yi. Yeah. So 1 minus yi is being multiplied with log of this numerator minus this denominator, and after just simplifying it, see what
Helping
the
because
result is there.
this can be is so there is a 1 minus.
See, in order to excel in this course, like you just need to have a conceptual understanding, like what each algorithm does, how the derivation comes, and what are the key conclusion that comes from the derivation and their respective formulas. Right. Mm, you just need these 2 to 3 things, and you will be good to go.
Yi, the log of e power minus w transpose xi will become 1 minus yi. The log and the e in the numerator will cancel. It will be minus w transpose xi. There is a minus log 1 plus e power minus w transpose xi, right? So that comes from this 1 multiplying the log of the denominator. So that is this term. So the other term which remains is 1 multiplying the numerator, which is okay. So which is what we took as this, right? So 1 minus yi into the numerator was this, and 1 multiplying the denominator is the second term. So now yi multiplying the denominator would just be yi log of 1 plus e power minus w transpose xi, which will cancel the first term out, right? So 2 terms get cancelled and the remaining is just this, right? So this is what we have. Now what we want to do then is maximize this with respect to w, right? So our goal is now to find an estimate for w is to do the following, right? So maximize with respect to w, sum over I equals 1 to n, 1 minus yi minus w transpose xi minus log 1 plus e to the minus w transpose xi, which is exactly this. I've not changed anything here. Now, because there is one of the terms is easy, it's a linear in w. The other term has this log of some 1 plus e x, which if you take the derivative and try to set it to 0 with respect to w, of course, take the gradient with respect to w, set it to 0, you will not get a closed form expression in a nice closed form expression for this problem, right? So we cannot solve this problem in closed form, in an analytical form, right? So no closed form expression, that is, there is no formula for w from solving this problem, because we can always solve this using the method of, let's say, gradient descent, right? So where if you're doing maximization, then it will be gradient descent. Nevertheless, we can do a gradient based algorithm to solve for w, which means that you start at some point, some guess for w, and then iteratively improve the guess by moving along the direction of the negative gradient if you're doing a minimization, and moving along the positive gradient if you're doing a maximization with some step size, right? So we know that that's how one typically does gradient descent. Okay, so because there's no closed form expression, what we're going to do is we're going to go ahead and evaluate the gradient for this problem and see what happens, right? So can perform gradient descent or ascent if it's a maximization problem, depending on whether we want to write it as a max problem or min problem. We will do gradient ascent or descent respectively. So it's instructive to look at the gradient of this problem, so that will give us some insight. So let's do that. So this is log likelihood of w. So I can look at the gradient of the log.
Okay, so these things are very intuitive. I don't know. I should go and reiterate like what is the gradient of a vector, right? So let's say there is a function. Let's say let's say there is a function having three parameters x, y, and z. Okay, and we need to find the gradient of this f. So the gradient of this f is defined as a vector such that first of all we will take the partial derivative of this function, that is del of f divided by del. Sorry, it is not d, it is del, because we are doing the partial derivative. Yeah. And then del of f divided by del of y and del of f divided by del of z.
log likelihood of W and see how that looks like. Well, that's going to look like the following, right? So this is sum over I equals 1 to n 1 minus Wi into minus xi. That would be the first term's gradient with respect to W minus, well, what is the log of 1 plus e to the minus W transpose xi gradient? Well, that is going to be 1 by 1 plus e to the minus W transpose xi, because log of anything we get a 1 by this thing. And now I'll have to take the gradient with respect to e to the minus W transpose xi. Well, that is chain rule. So that would be simply e to the minus W transpose xi. And now again, using the chain rule repeatedly, I'll have to do it for minus W transpose xi, which will give me minus xi. Right. So this is the gradient with respect to W. So this is going to be sum over I equals 1 to n. This is the gradient W transpose xi, and now again using the chain rule repeatedly,
Okay, so remember there is like you could think like, hey, I like there is three variables right here involved, right? And that is yi, xi, and there is w. So with respect to which we should take the gradient. So the idea is very simple. The thing that we are trying to minimize or maximize, we will always take gradient with respect to that. That's the idea, right? And if you need to understand why that's the case, so whenever there is a function, let's say there is a 2D function, a linear function, right, and there is some kind of curve like this. So this is a restriction of the mouse, right? This like sharp edges, right? So suppose this is a smooth curve, right? And we need to maximize or minimize the value of the function. So what we does is we used to take the derivative with respect to the with respect to the independent variable, right? We always take derivative with respect to the independent variable. The similar concept is here also. The likelihood function is just the likelihood function is a function of w, right? Is a function of w, and you know the xi and yi are are given to us. They are just constant. So we need to divide. We need to take the derivative with respect to w only. That's the concept.
I'll have to do it for minus W transpose xi, which will give me minus xi. Right. So this is the gradient with respect to W. So this is going to be sum over I equals 1 to n yi xi, right? So yi xi, first I write the minus xi plus yi xi plus this is xi e power minus W transpose xi by 1 plus e power minus W transpose xi. Right, so this is what we have at this point, which can further be written nicely as the following: I equals 1 to n yi xi minus xi into, so this is going to be 1 minus this term, because that has xi common. So if I take 1 minus this term, well, that's just going to be 1 divided by 1 plus e power minus W transpose xi. Right, so which is finally has a nice form, which is just sum over I equals 1 to n xi into yi minus 1
So
by 1 plus e
you will this step is quite easy, right?
power minus.
We are just taking minus xi as common right here. So it will be like minus xi, from here 1 will come. So 1 minus this whole term. this whole term, right? 1 minus this whole term. So this will go in the this will go and multiply with 1, and there is a minus of this. So this two value will cancel out in the numerator, and the denominator remains this only. I hope you got the point.
W transpose xi. Right. So this is the gradient with respect to some w of the original likelihood function, and we would want to maximize this, which means that the gradient ascent update rule would look like this: wt plus 1. Right. So this is the gradient update rule. Wt plus 1 will be Wt plus eta times the gradient of the log likelihood of w, right? So because it's a maximization problem. If it was a minimization problem, then it would be minus eta times the gradient, right? So here you are moving along the gradient direction using some step size eta t, right? So this is the step size.
Very
Step size.
intuitive.
Typically, one can use a step size that goes down to 0, something like 1 over t, right? So would be a reasonable step size or some constant over t. That can be step size. But what is this whole thing telling us now, right? So this is then Wt. So let me put it this way: plus eta t into the gradient term, which we just computed as sum over I is 1 to n xi yi minus. Well, what is this? So this is 1 by 1 plus e power minus w transpose xi. So this is my gradient update term rule. Now, if you look at this, there's something interesting happening here, right? So this gradient is instructive to study this gradient. Now, this yi is just 0 or 1. It's just a label in your data set for this point 0 or 1. Now, this term 1 divided by 1 plus e power minus w transpose xi is what is that? Well, that is the probability, which is just g of w transpose xi. Right? So this is just what we think is the probability that this point is 1. Now, what is the gradient then telling us, right? So what is xi? Xi is of course points in d dimension. What is the gradient telling us? First thing to notice here is that the gradient is actually a linear combination of our data points, because we are summing up over all
So you can think this thing is like this will be either 0 or 1. This yi will either 0 or 1, and this will take value from 0 to 1. So it is either 0 or 1, but this is from 0 to 1. Like I think you got again, because
data points.
what I mean to say is like that. Yeah. So yi is 0 comma 1, whereas the z of z is 0 comma 1, close. That is the z of z is any fractional value. It will kind of take any fractional value, and this y of I will take either 0 or 1. That's all. So this whole product will become something constant, and a constant is being multiplied with xi, right? So this red term, this red expression will somewhat, it will look like a x1 plus say bx2 plus c x3, right? Where a b c are just scalars, nothing fancy.
Points xi times some constant, right? So I can, this is just a number, right? So yi minus 1 by 1 plus e power minus w transpose xi, I can treat this as some theta I, right? So this whole thing is summation over I equals 1 to n theta I xi, where theta I is some number, xi is a vector in Rd. So basically what I'm doing is a linear combination of my data points. Now, that's the first observation. The second observation is that now the gradient, how does each data point contribute to the gradient depends on how well my current guess for w approximates the probability of the label y, right? So for example, if for a given point, if the label is actually 1, right? So let's say I observe a label as 1, and with respect to the current w, the probability that this point can be labeled. Now the gradient, how does each data point contribute to the gradient depends on how well my current guess for w approximates the probability for the label yi, right? So for example, if for a given point, if the label is actually 1, right?
Okay, so let's have a just a minute of 1 minute like that.
So let's say I observed a label as 1, and with respect to the current W, the value approximates the probability of the label ya, right? So for example, if for a given point, if the label is actually 1, right? So let's say I observed a label as 1, and with respect to the current W, the probability that this point can be labeled 1 with respect to the current W, right? So because we are iteratively doing this at some W, at some t iteration WT, right? So in fact, I should put a t here, just to be, there has to be t here because it's the gradient at WT, right? So that's what we are evaluating here. So at our current W, what is this telling me? This is telling me what is the chance that this point will be labeled plus 1. If the chance is high and the point is actually labeled 1, then this difference is actually, and the approximates the probability for the label ya, right? So for example, if for a given point, if the label is actually 1, right? So let's say I observed a label as 1, and with respect to the current W, the 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 probability that this point can be labeled 1 with respect to the current W, right? So because we are iteratively doing this at some W, at some tth iteration WT, right? So in fact, I should put a t here, just to be, there has to be t here because it's the gradient at WT, right? So that's what we are evaluating here. So at our current W, what is this telling me? This is telling me what is the chance that this point will be labeled plus 1. If the chance is high and the point is actually labeled 1, then this difference is actually theta I corresponding to that point is going to be a small labeled plus 1. If the chance is high and the point is actually labeled 1, then this difference is actually theta I corresponding to that point is going to be a small number, right? So it's going to be 1 minus, let's say this chance was 0.99. So that value is going to be 0.01, which means that that point is not going to really affect my gradient. Now, on the other hand, if the label was 1, but then my chance that it is being labeled as 1 by the current WT is 0.1, right? So which means that you are more likely thinking that with respect to the current W, this point should actually be negative, labeled -1 with 90% chance, only 10% chance you give it for +1. So now that's a mismatch between the label and your current guess, right? So which means that the next W that you get will be influenced more by the points where you are making mistakes right now, right? So because that's what is happening, because that yi minus g of WT xi will be high when there is a mismatch, and yi minus g of WT xi will be low when there is no mismatch, which means WT correctly classifies my current point, right? It's of course never going to be 0 because this probabilities will never be 0 or 1 exactly, but then that doesn't matter, right? So as long as it is too small, then the point does not matter to the next W, so that you'll kind of move in the direction so that you are concentrating more on points where the current W is making a mistake, right? So that is
Okay, uh, just give a bit focus here, like, so this is kind of a little bit non-intuitive, but if I tell you the simple idea is like, if our if our model, means if our current WT is making prediction wrong, then we will give more weightage to xi. If my current if my current WT is classifying up xi wrong, then we will give weightage to this xi. Otherwise, we will give less weightage to the xi, right? And that all is encoded in this expression, the red expression. That's all is encoded in this expression, nothing more. So this is nothing but you can think of like, it is y hat. In fact, you can't say it is like y hat. Why? Because y hat should be either zero or one, right? So it is not y hat, but it is actually a continuous score, and for a correct classification, this means for a correct classification, let's say this yi will have to be, then for that classification, this value will be higher. So 1 minus something higher, that is something around 1, will be less. And if this, and the other case for correct classification could be this
the gradient.
yi is 0, right? And this value also turns out to be around 0. So the again this the difference between these two will be small. So we are just simply giving less weightage to those points which are doing good, means for which our model is doing uh, perfect work, and we are just penalizing the exercise which are wrongly interpreted, right?
And intuitive update rule for this gradient descent in this case. And this algorithm, as we said, is called as a logistic regression algorithm, which is a very popular, simple algorithm, but then a very popular algorithm because you can run it easily. Of course, there are other, second order methods. We just use a gradient descent or an ascent to solve this problem. There are more sophisticated methods also that you can use to solve this problem. One of
Okay, so remember that the gradient descent problem is like a first order differential. Yeah, so it is analogous to first order differential in calculus of a single variable. And when we talk about the Hessian matrix, then we take a double derivatives. So it is like mm, so it's like second order derivative or in the higher order.
the methods again is using the IRLS technique, which is an iterative reweighted least squares method, where you kind of solve a successively least squares problem to get to the original W. We're not going to see that, but just be aware that there are more faster methods to solve this than the vanilla gradient descent or ascent type of methods. But for our purposes, here's a nice model which will allow any data set and you can get a W. So what you do after you get the W, well, you'll use the W and do the prediction sign of W transpose Xi. Right? So for X test, if I get an X test which is in RD, now W hat is the solution that the gradient ascent converges to, then I'll just
Hello friend who is there in chat. Hello to you.
to W transpose X test, and then I'll predict a sign of this. Right? So this would be my y hat test as usual, right? So I'll just predict it using this. But now, because this algorithm has probabilities, right? So this would be my y hat test as usual, right? Right, so I'll just predict it using this. But now, because this algorithm has probabilities implicitly embedded in it, you not only get a prediction, you also get a what you do after you get the W, well, you'll use the W and do the prediction sign of W transpose Xi, right? So for X test, if I get an X test, which is in RD, now W hat is the solution that the gradient ascent converges to, then I'll just do W transpose X test, and then I'll predict a sign of this, right? So this would be my y hat test as usual, right? So I'll just predict it using this. But now,
Yeah, so you should notice that the signum function here used and this is the sigmoid function. These two things are very different. Don't be confused at these two different functions, right? So means yeah. So this is the signum function. Let me
because this
see.
is in RD, now W hat is the solution that the gradient ascent converges to, then I'll just do W transpose X test, and then I'll predict a sign of this, right? So this would be my y hat test as usual, right? So I'll just predict it using this. But now, because this algorithm has probabilities implicitly embedded in it, you not only get a prediction, you also get a probability, which can be thought of as a confidence with which you're actually making this prediction. That's one of the major advantages of this model, because the probabilities are inbuilt in this model, so the predictions can be made with certain confidence and so on, right? So this is this is the first thing that I want to say. A couple of more points which I wanted to mention about this algorithm is that there is a kernel version for this algorithm that one can derive. This version that this test, which is in RD. Now W hat is the solution that the gradient ascent converges to. Then I'll just do W transpose X test, and then I'll predict it as sign of this. Right? So this would be my y hat test as usual, right? So I'll just predict it using this. But now, because this algorithm has probabilities implicitly embedded in it, you not only get a prediction, you also get a probability, which can be thought of as a confidence with which you're actually making this prediction. That's one of the major advantages of this model, because the probabilities are inbuilt in this model, so the predictions can be made with certain confidence and so on, right? So this is this is the first thing that I want to say. A couple of more points which I wanted to mention about this algorithm is that there is a kernel version for this algorithm that one can derive. This again can argue that your W, the optimal W, should be a linear combination of your data points, and so because of this fact, now you can derive a kernel version for this problem, right? So if you substitute this form into the objective, then you can write this in terms of X transpose X, and so that can be kernelized, right? So we won't do that, but it's good to be aware that this can be used to derive a kernel version of this algorithm. The fact that W has to be in this form, the formal again, this is just for your understanding, for your knowledge. We are not going to delve deep into this also, but then the formal theorem here is called that guarantees that W will be as a linear combination of your data points. W meaning W star, right? So that solves the logistic regression problem, has to be of this form. This is called as the representative theorem, right? So for those who are curious, you can look up representative theorem. Right, so now we can derive a kernel version for logistic regression, which is
So we don't need to focus on this portion of this lecture, right? Just forget it, like it does not exist at all.
Is another good thing. In practice, what people also do is kind of look at like a Bayesian version of this, which is a regularized version of logistic regression, regularized version, which is also very popular in practice, where you would do minimize over W. Now you write this as a minimization problem. Sum over I equals 1 to n. Now the maximization objective here will now get converted into a minimization objective, which will become here sum over I equals.
Okay, so in this expression here, like in this expression, you just need to remember that the solution in case of logistic regression, that is the parameter W, turns out to be the linear combination of xi. This might be asked in a question like uh, uh, there is given four statement and you have to pick which is the correct statement, right? So that type of question might come here.
So that is
Just remember that W is simply the linear combination of all the xi, that is the feature variables.
the gradient intuitive where you would do minimize over W. Now you write this as a minimization problem. Sum over I equals 1 to n. Now the maximization objective here will now get converted into a minimization objective, which will become log of.
You don't need to remember all this function in. I think we will figure out like which formula to recall. Means remember in case of during examination. Right? We don't need to figure all or learn all these steps that sir has gone through.
And you can get a W. So what you do after you get the W? Well, you'll use the W and do the prediction as sign of W transpose xi, right? So for x test, if I get an x test which is in RD, now W hat is the solution that the gradient doesn't converges to, then I'll just do W transpose x test and then I'll predict a sign of this. Right? So this would be my y hat test as usual, right? So I'll just predict it using this. But now because this algorithm has probabilities implicitly embedded in it, you not only get a prediction, you also get a probability, which can be thought of as a confidence with which you're actually making this prediction. That's one of the major advantages of this model, because the probabilities are inbuilt in this model, so the predictions can be made with certain confidence and so on, right? So this is this is the first thing that I wanted to say. A couple of more points which I wanted to mention about this algorithm is that there is a kernel version for this algorithm that one can derive. We are not going to go deep into this also in a for logistic regression, which is another good thing. In practice, what people also do, minimize over W. Now you write this as a minimization problem. Sum over I equals 1 to n. Now the maximization objective here, the first term plus W transpose xi into 1 minus y. Right, so you can do this, plus you do a regularization using our usual L2 norm regularization. Right, so this is the regularizer. Of course, you can use a cross validation parameter that we have discussed earlier to, right, so to cross validate. Right, so this is cross validation.
So seeing this regularization, you should recall that this is kind of like this is kind of ridge regularization, where we regularize using the norm 2 of W vector. Means the norm 2 length of means that is the Euclidean distance. We consider the Euclidean distance of this W, right? Something of a ridge regularization.
Hyperparameter. It's not hard to derive the gradient rule for this as well. It's very simple because it's the previous gradient plus just lambda times W, right? So you can still perform gradient descent very efficiently for this regularized version as well. Okay, so with this, I want to summarize this new algorithm that we have seen, which is the method of logistic regression. It's a very popular algorithm in practice. One of the things that it does well as with respect as against perceptron is that this will allow this can model any data set, right? So no matter if the data set has outliers or not. Of course, if the data set has more structure, more than linear, then you can look at a kernelized version of this algorithm as well. So in practice, of course, perceptron has the disadvantage that it works only for linearly separable data set. This algorithm does not. It will converge to a reasonably very good W that you can then use for testing for new data points. But it does not try to, I mean, it has its own way to find out the W, right? So which maximizes the likelihood of observing the data under a certain model that you put out. But as I said earlier, perceptron gave us some mistake bound, and that mistake bound merits a longer discussion because we can look at that mistake bound and then derive a more direct algorithm which depends on certain aspects that mistake bound to tell us, specifically about the margin, right? So the next time we see, right, so what we're going to see is that we have logistic regression, which is a powerful algorithm on one side. We will develop another algorithm, which is a very, very elegant algorithm, which also is very powerful and works really well in practice, especially for structured data. And this algorithm is called as a support vector machine algorithm, and that will we will derive inspiration from perceptrons mistake bound to develop that algorithm. That we'll see starting next time. So this time we will finish with logistic regression, and I hope to see you again soon. Thank you.
Yeah, so this lecture is quite heavy in maths. Like there is a lot of math stuff have been encoded in this lecture. So I think I need to revisit this lecture a couple of times. But there is nothing rocket science have been gone involved in this lecture. Just a couple of repetition and you will be good to go. And as we will solve QIQ, then we will figure out which particular position or which particular formula we should recall, right? Not recall, we should have a note of. Yeah, so I am kind of tired by now. The legs are being fatigued already.
And decision trees, which are discriminative because hello and welcome back. So far, we've looked at several supervised learning algorithms, including perceptron and the logistic regression algorithm. And now what we're going to do today is revisit perceptron and see some of the properties of perceptron that we spoke about earlier, and see how that leads to a more principled and elegant formulation for coming up with a new supervised learning algorithm. So let's start by
Break of 2 minutes.
Recalling that for the perceptron algorithm, the number of mistakes that perceptron makes depended on a quantity which we called as the radius margin bounds, which was as follows. The number of mistakes was at most r squared by gamma squared, where r is just the radius of the data points, right? So where what was r squared? Well, if you had a data set such that all of norm of xi squared is less than or equal to r squared, then it's basically saying that there is a big ball of radius r and all the data points are within this ball. More importantly, gamma is the assumption that we made about the data set, that the data set is linearly separable LS with margin gamma. What does that mean? That means that for there exists some W, right? So whatever we call it as W star, such that W star transpose xi into yi was greater than or equal to gamma for all the data points I, where gamma is some value greater than 0. In pictures, this meant the following, right? So that if you had a data set like this, well, if you had a W star like this, then it means that, well, maybe this is some line such that the set of all x such that W star transpose x equals gamma, and this is the line such that the set of all x such that W star transpose x equal to minus gamma. Then what we are saying is that all the positive points are lying either on the line or to the right of this line, and all the negative points are lying either on the line or to the left of this line, right? So this condition that W star transpose xi yi is greater than or equal to gamma just means that, there is this separation between the positive class and the negative class, which is given by this non-zero gamma. And that was crucial because we also saw an example where if the separation was not there, then perceptron may not converge. Now, if the separation is there, we proved that perceptron indeed converges, and it converges with a finite number of mistakes. Of course, finite number of mistakes implies convergence, and we have bound on the number of mistakes perceptron makes, which is r squared by gamma squared. Now, there are a couple of important points that we need to talk about here with respect to, what does this mean? That
Yeah, so you should remember this formula of mistakes, right? The number of mistakes should be uh, upper bounded by r square by gamma square. This is an important formula.
you converge with number of mistakes at most r squared by gamma squared, right? So the first point that I would like to talk about is the following, right? So quality of final solution, the quality within quotes. What do I mean by this? Well, let's take an example to illustrate this point. Let's say we had positive points which were all, let's say, here, something like this, something like this, right? So let's say this was our data set. Now maybe I'll add a few more points here. Now, this is a linearly separable data set with some gamma margin. Now let's take a W which is pointing in this direction, right? So let's call this W star. Now this W star implies that the line that separates the positives from the negatives is going to be this line.
Okay, note that the gamma will be kind of symmetrical about this linear separator, right? If we draw a linear separator passing to the origin, then it should be kind of symmetrical in both the left and the right, and parallel to that linear separator.
Right, so it does separate the positives from the negatives, right? So the data set is linearly separable. Not only that, it's in fact linearly separable with some gamma margin, and that gamma margin comes from the fact that you have this line which is parallel to this W star on one side, and this line which is parallel to W star on the other side. So this is just a set of all x such that W star transpose x equals, let's say, some gamma, and this is the set of all x such that W star transpose x equals minus gamma. Let's say this is our data set. So this data set is linearly separable with gamma margin. Now, it is not necessary that this is the only W star that separates this data set with some margin. Well, for example, I'm going to show you another W star, another direction which also separates this data set with some margin. Now, can you already think of a W2 star, right? W star 2, right? So a different direction which also separates this data set with some other margin. Pause and think about this. I'll tell you one example. So here is one example, right? So just look at the direction which is the x-axis direction. Let's call this W star 2, right? So this is another W star, which all, let's call this W star 2. Right, so this is another W star, which also separates our data set, because this would be, in fact, the y-axis would now be the separating line, and all the green points are on one side of the y-axis and all the red points are on the other side of the y-axis, so that the x-axis direction is also a valid direction. It also separates our data set with some margin. Now, one can ask the same question: what would be the margin for this particular W star 2? Right. So now, if you look at it, it's going to be like this. Right. So this would be the margin for W star 2. Here it would be for this. Right. So this would be the margin for W star 2. Sorry about that. Yeah. W star 2, right? So basically what has happened is that you have two different W stars, right? So one with a separation given by the blue shaded blue region,
because the first red point is here with respect to the blue, with respect to the blue separators, right? So that's the margin, that's the amount that W2 star has, whereas if you look at W1 star, it separates, sorry, I should use a different color, it separates the same data set with a larger margin, right? So now one might ask the question, among these two W star and W2 star, which one would you prefer if you were given this data set a priori? Well, somehow intuitively it feels that W star is a better separator for this data set than W star 2, because it separates the data set, that direction separates the data set with a larger, so to say, margin, right? Now let's go back and ask, what is
The idea is simple. The larger the margin, the better our model parameter is, right? Why? Because we are like in the navy blue colored, right? For this navy blue colored uh, W, we are quite confident that okay, if a point lies like someone here, the distance between these two margins determines the confidence with which the model is trying to predict. The greater the margin, the greater we have the probability, okay, that it's like positive and it's like negative. So you can think of like if I draw a line, like if I draw a straight line, means a number line.
the
If we draw a number line like there, so in this region the probability of predicting the point at negative is very high. In this region the probability is very high, but in this region is kind of ambiguous, right? This In this region the probability of positive is low, as well as predicting the negative is also low. So this is kind of ambiguous region. So the lesser this ambigu no no no
because it separates the data set, that direction separates the data set with a larger, so to say, margin, right? Now let's go back and ask, what is the mistake bound of perceptron telling us in this figure? It is telling us that the number of mistakes is at most r squared by gamma squared. Well, now when we argued this gamma square, right, so we just assumed that there is some W star which separates the data with some gamma. We did not say anything else about this W star, right? So we just assumed that there is some W star, which means that in this data set, yes, there are two different W stars with two different gamma 1 and gamma 2 perhaps, but because we did not make any other assumptions about the true W star, well, the number of mistakes will depend upon the best possible W star's margin, right? So which means that the observation is the following, right? So the number of mistakes depends on the best possible W star's margin. Remember, for the perceptron algorithm, we assume that W star had norm 1, right? So here both these W star and W2 star are on the unit circle. We can make that assumption. But then one has a smaller margin. Let's say this gamma was just, maybe this gamma was 10, whereas this gamma was just 1. Now what we're saying is that, well, though W2 star classifies it with only margin 1, the number of mistakes is going to depend on the one that has the largest margin, right? Because we did not make any assumptions about the specific W star. It could be any W star. Hey, here is a W star with the large margin gamma equals 10. And so the number of mistakes are going to be bounded by r square by 10 squared in this case, right? So which means that if there is some W star which separates your data set with a large margin, then the number of mistakes that perceptron is going to make is going to depend on this large margin, large number, and it's going to be inversely proportional, which means that larger gamma squared is smaller is going to be the number of mistakes, right? So because this is an upper bound, right? So which means that it has to hold for any W star with its corresponding margin, and we want to and so the W star with the largest margin, which will imply the tightest upper bound, right? So what we are essentially saying is that the number of mistakes of perceptron depends on the best possible W star's margin, right? So in this case, it's going to depend on the orange line. This is observation 1. Observation 2, though, is very important in the sense that though the number of mistakes is going to depend on the W star which has the largest separation margin, the W that perceptron is going to output at the end need not necessarily be that W star which separates the data with the largest margin, right? So why is that? Because there is nothing in the algorithm that is really driving it towards finding a W star or W that the perceptron outputs, right? So let's call that, W perceptron, PERC, right? So this is what perceptron outputs. Now this W perceptron need not necessarily be W star which has the largest margin. Why? Because perceptron has nothing inbuilt in the algorithm, in the update rule, that says that you want to find a W where the margin is as high as possible. What we just argued is that, well, the update rule that perceptron uses is enough to argue that if there is some W star with a large margin, then the number of mistakes that perceptron will make is small. However, the output W perceptron that perceptron finally gives you need not necessarily be, in this case, the orange line. It could be the blue line also, right? So W perceptron need not necessarily be W star. It could be W star 2 also, the blue line.
Yeah, so this point is very like kind of important, like why we prefer SVM, or yeah, why we prefer SVM over perceptron algorithm, or like what is the drawback of perceptron algorithm. You can then in this within this kind of concepts, this point will help us. So the perceptron will just find a line, whether it is separating with a higher margin or lower margin. That is not concern of the perceptron algorithm.
Right? So why? Because the moment perceptron finds W star 2, right? So as it runs the algorithm, it's immediately going to see that, hey, for W star 2, it's no longer making any mistakes with respect to the data set. It's just going to stop the algorithm there and say that it is converged, right? Now, then, is that a contradiction? It's not, right? So why is it not a contradiction? Because what we're essentially saying is that if there is a W star with a large margin, then it means that the problem is inherent.
So like you could think like if you have used Kaggle, right? So you have developed an algorithm, developed a model, and you train that model and see that okay, for the training data set, this model is working quite well. The blue model is working, the blue margin is working quite well, right? But when it comes to the test cases, when it comes to test cases, then this model will definitely make more mistakes with respect as compared to the one with a W star, right? So the yes, sky blue one will have a high generalization error, in case whereas this navy blue colored will have less generalization error.
Inherently simpler, because the class of +1 and -1 are separated, well separated, and so perceptron makes fewer mistakes to figure out some line that separates the plus from the -1. It does not mean just because the problem is simpler, perceptron is going to find that separator which separates it with the largest margin. No, that's not necessarily true, because there is nowhere in the algorithm where we have specifically said that you want to find a W that separates the data with the largest margin, right? So these are two important points that we want to make about perceptron. Now, what is this kind of telling us is that though intuitively it feels that we want to find a separator which kind of separates our positives and negatives with as much width as possible, your perceptron may not necessarily find it. Though perceptron is a super simple update rule, it does not have the power to find a W star that separates the data with the largest margin. So then we ask the question, well, here's the question that we are going to ask now. Now, given that we prefer separators with large margin, right? So classifiers or separators with large margin, can we directly find them? So what we want to really do now is that, well, we want to let go of perceptron and then directly focus on the problem that, well, given a data set which is linearly separable, can we directly find a W star which separates this data set with as large a margin as possible? Right? So maybe that is the question that we would directly want to ask, instead of saying that.
Okay, so you can notice the transition of the problem statement. So earlier the problem statement was like, okay, we need to just find a classifier, any classifier that could potentially distinguish from the positive from the negative. If we are able to find that, then we are fine, right? But in case of the further algorithm which sir is going to discuss, we will discuss like uh, a way to find a classifier which maximizes this margin.
We'll find some separator. Let's find a separator which is actually good. Now, intuitively, we understand.
Okay, so note one thing like if the margin is higher, the upper bound is lower, right? The margin is higher, the upper bound is lower. As a result, the perceptron algorithm will make a relatively mistake as compared to the one with the smaller margin. So you can think, in fact, it could be argued that the perceptron will converge faster in case of one with have larger margin. So remember this point.
Understand that this is important. This seems like the orange line is a better line than the blue line. But so when I say orange line, I mean this separator, of course, right? Yeah. So this has a larger margin. Now, why is that true, right? So why would we want to prefer the orange than the blue separator? Well, one way to think about this is the following, right? So now, again, for this data set, the blue line has a very thin margin, whereas the orange one has a large margin, a broader margin. Now, what is the implication of that? Well, the implication of that is that, if you kind of perturb your data set a little bit, right? So maybe add some noise to this data set, right? So which means that,
Imagine that there is some noisy version of this data set that you might see in the
test data. Now, if you have a broader margin, then you are going to be tolerant to this noisy version of the train data, because even if you add noise, you're still going to be on the right side of the separator. So what do I mean by this? Right? So let's take an example. Maybe there was a point which was somewhere here, and now I add some noise that this point moves here, right? So this negative point, after adding noise, moved to this point, the new point that I have circled in red. Now, if this was my test point, now the blue separator would say that, well, how am I going to make a prediction? I'm going to make a prediction either using this line or using this line, depending on which W I use. Now, if I use the blue line, then the circled red point is going to be predicted as positive, because it is on the right side of the blue line, whereas it's still on the left side of the orange line, of this line, right? So in other words, even if the test is a noisy version of the train, right? So you still have some leeway which this margin provides you, which takes care of the generalization ability of our algorithm, loosely speaking, right? So in some sense, the larger the width or the margin that we can ensure for our W, the more robust that line is, right? So if you have points close to the margin, then close to the separator, right? So then small change might not affect the label so much, right? So that's the goal. That's the reason why we prefer lines with a larger width. But how can we formalize this, right? So this is the informal way to write this question, that given that we prefer classifiers with large margin, can we directly find them? So what we're going to do today is to, our goal is to come up with a principal
points with as large a margin as possible, right? So let's start with that goal, right? So this is going to be our goal now.
goal, to come up with a formulation that, so how can we do this, right? So guys, we can do it as follows, right? So we want to maximize, gamma, you want to find a W that maximizes the margin as much as possible, right? So the parameters of our algorithm are W and gamma. You want to find a W that maximizes the margin as much as possible, right? So the parameters of our algorithm are W and gamma, and we want to find a W and gamma such that gamma is as large as possible, but we cannot allow all possible Ws. We will only allow Ws
which linearly separate the data set with gamma margin, right? So which means that such that
W transpose xi into yi is greater than or equal to gamma for all I, right?
So what are we saying here, right? So we want to maximize the margin as much as possible, that gamma value, such that for your data, the W that this algorithm, this formulation outputs has to have the property that W transpose xi yi is greater than or equal to gamma. That is, all the points are on either side, either on the right or right side of the line given by the equation W transpose x equal to gamma, or on or left side of the line given by the equation W transpose x equal to minus gamma. That's what this formulation is telling us. So I think this is a good time to pause and think, is this really specifying exactly what we want, or are we missing something about this formulation?
And one thing which I could think of is missing, like the condition of
Now, let me tell you what we are missing about this formulation now, and that will give us a slightly different way to think about this. Now, so what we are here saying is that, let's say I have some W, right? So let's say this algorithm outputs a W, and now, why did this algorithm output a W? That W had the largest gamma. What does that mean? That means that
W, first of all, satisfies W transpose xi yi is greater than or equal to gamma for all the data points, which means that let's say gamma was some value 5. So which means that this is the line set of all x such that W transpose x equals 5, and this is the set of all x such that W transpose x equals minus 5. So which means that this algorithm is now going to say, well, here is the W which is the answer to this problem, and the gamma corresponding to this W is, let's say, 5, right? So this is what the algorithm outputs, let's say. Now this equation is W transpose x equals 5. The moment you tell me that, hey, here is the W and this is the corresponding gamma, now what I can argue is that look at the corresponding W, which is, let's say 2 times W transpose x equals 2 times 5. If every x on the line satisfies W transpose x equals 5, then every x on the line also satisfies equals 2 times 5. If every x on the line satisfies W transpose x equals 5, then every x on the line also satisfies 2 times W transpose x equals 10. Naturally, right? So it's just scaling both sides left and right by 2. So this is also true. Now this means that now here is another W, which is W dash transpose x equal to 10, where W dash has the property that it linearly separates the data set with margin 10, right? So with gamma is 10. So which means that if you had given me W and 5 as the answer and claimed that that is the answer to this problem, now I'm saying that it cannot be the answer because you can scale W by 2 times and then the gamma also scales up, right? So which means that now you can keep scaling W infinitely such that the gamma can grow up to infinity. So which means that if I solve only this problem, it's not sufficient because the issue is that we can scale W arbitrarily. So this is not going to be a useful formulation because W can grow arbitrarily. So we have to ground W. How can we do that? Well, one simple way to do that would be to just say, like how we did in the perceptron's assumption, that we are not going to allow all W's, we are only going to allow W's which have length 1, which means that our modified formulation is going to be maximize over W and gamma such that W transpose xi into yi is greater than or equal to gamma. Nothing changes so far, but then we are only going to allow W such that norm of W is 1, right? So which means that I cannot scale W, right? So the moment I do W to 2W, then the length of W changes. The norm squared kind of becomes 4 times, right? So because I'm scaling W by 2, the norm squared becomes multiplies by 2 squared, which is 4. So it's no longer going to be 1. So which means that 2 times W is not going to satisfy this condition, so that we cannot just arbitrarily scale, right? So this is a possible solution to this problem, right? So we can try to solve this problem and then we will get some solution, right? So this is a reasonable formulation to solve this problem. But now, I mean, one can definitely solve this problem and using optimization techniques, and you will get a W and gamma. There is no doubting that. But one can ask if we really have to have these 2 variables in this formulation. There are 2 variables that we are maximizing over, W and gamma. Whereas if you really see, right, so you are only searching for W's with unit length, right? So which means that in 2 dimension, what this means is we are just looking for W's. So we are just looking for W's with length 1, right? So now if you have a data set, let's take another data set, simple data set, let's say plus minus. Now let's say we are only looking for W's in the unit circle, on the unit circle. Maybe this is a W. Now the moment I fix this W, which means that I'm fixing the direction, the length is fixed in that direction. What happens is, with respect to this data set, the moment that the direction is fixed, the length is fixed because we are only looking for length 1, the gamma corresponding to this is fixed. The data set will decide what the gamma is. For this W, let's call this W1, the gamma is fixing the direction. Let's say we are only looking for W's in the unit circle, on the unit circle. Maybe this is a W. Now the moment I fix this W, which means that I'm fixing the direction, the length is fixed in that direction. What happens is, with respect to this data set, the moment that the direction is fixed, the length is fixed because we are only looking for length 1, the gamma corresponding to this is fixed. The data set will decide what the gamma is. For this W, let's call this W1, the gamma is going to be, what is the equation of this line, right? So set of all x such that W1 transpose x equals maybe 5, right? So if it is 5, then 5 is the gamma. So similarly, I can search for a W in this direction of length 1, which means that this would be my separator. And again, the data set will tell me what the gamma is. The gamma is in this case is going to be this equation of this line, which is the set of all x such that maybe this is W2 transpose x equals 3. Right? So maybe this is my gamma. So the gamma is in fact a function of your W. The moment I fix W, the gamma is fixed. Now what we are doing in the previous formulation is that we are maximizing over both W and gamma, but then gamma is just a function of W. Now the way we got out of the problem that W can be scaled arbitrarily is by grounding W, length of W to be 1. The other way to solve the same problem is to say that, well, I'm not going to only search for W's which have length 1. I'm going to throw that away, right? So I'm going to say that I don't have the condition that norm of W square is equal to 1. But the moment I throw the condition away, I can scale W arbitrarily, right? So which means to increase gamma. But now what I'm going to say is that I'm going to ground gamma. I'm going to say that, well, gamma is always going to be equal to some constant. For example, constant is 1, right? So what does that mean? That means that, I'm still going to search in each direction gamma. But the moment I throw that condition away, I can scale is equal to 1. What a function of your W. The moment I fix W to this W1 fix. Let's say we are only looking for W's in the unit circle, on the unit circle. Maybe this is a W. Now the moment I fix this W, which means that I'm fixing the direction, the length is fixed in that direction. What happens is, with respect to this data set, the moment that the direction is fixed, the length is fixed because we are only looking for length 1, the gamma corresponding to this is fixed. The data set will decide what the gamma is. For this W, let's call this W1, the gamma is going to be, what is the equation of this line, right? So set of all x such that w1 transpose x equals maybe 5, right? So if it is 5, then 5 is the gamma. So similarly, I can search for a w in this direction of length 1, which means that this would be my separator, and again the data set will tell me what the gamma is. The gamma is in this case is going to be this, the equation of this line, which is the set of all x such that maybe this is w2 transpose x equals 3, right? So maybe this is my gamma. So the gamma is in fact a function of your w. The moment I fix w, the gamma is fixed. Now what we are doing in the previous formulation is that we are maximizing over both w and gamma, but then gamma is just a function of w. Now the way we got rid of the problem that w can be scaled arbitrarily is by grounding w, length of w to be 1. The other way to solve the same problem is to say that, well, I'm not going to only search for w's which have length 1. I'm going to throw that away, right? So I'm going to say that I don't have the condition that norm of w square is equal to 1. But the moment I throw the condition away, I can scale w arbitrarily, right? So which means to increase gamma. But now what I'm going to say is that I'm going to ground gamma. I'm going to say that, well, gamma is always going to be equal to some constant. For example, constant is 1, right? So what does that mean? That means that, I'm still going to search in each direction, but now the way it will look, this picture will look is as follows, right? So this picture for the same data set is going to look like this. The data set is the same, nothing has changed about the data set. It's still the same data set. Now if I want w1 in this direction, now what I'm saying is that, so this w1 has this line as, let's say, set of all x such that w1 transpose x equals 5. This was our earlier w1. Now this w1 I will not allow in my set of feasible w's. I'm only going to allow w such that the gamma is exactly 1. Now I can always get a w such that gamma is exactly 1, right? So if I find a direction which separates my data set positives from the negatives correctly, then I know that I can scale my w1 to make sure that my gamma is always 1. For example, in this case, I can always set w1 divided by 5 transpose x is equal to 1. This is also the equation of the line set of all x such that w1 by 5 transpose x equals 1. Now I can say that this is my w1 prime, which satisfies w1 prime transpose x equals 1, right? So in other words, I now have to scale down this w to this point, right? So in this direction, well, this would be w1 dash, and now with respect to this w1 dash, the same line will have gamma is 1, right? So which means that the moment I find a direction which separates my positives from the negatives, now I can scale the direction correspondingly such that these lines on which the data, I can push my data, I can push the lines parallel to this the line passing through origin as much as possible such that it fits the data points on either side. I can always scale my w such that these lines satisfy the equation that w transpose x equals 1, and on the other side w transpose x equals minus 1. Now because I can do this, now I don't have to worry about gamma. I can simply say that I will always set gamma to be 1. I'm only going to be searching for w's such that such a w will give me lines which are parallel to the line passing through origin, but then with gamma equals 1. Now if the moment I've grounded gamma, now it becomes a question of what am I trying to maximize. Earlier I was trying to maximize gamma. Now because I'm saying that I'm only going to search for w's such that gamma is 1, now what am I trying to maximize, right? So I now have to maximize this, this width, because that's what I'm trying to, make it as large as possible. Earlier we were saying that, well, that width when you fix w as gamma is 1, ground is says that I'm going to ground gamma. I'm going to say that, well, gamma is always going to be equal to some constant. For example, constant is 1, right? So what does that mean? That means that, I'm still going to search in each direction, but now the way it will look, this picture will look is as follows, right? So this picture for the same data set is going to look like this. The data set is the same, nothing has changed about the data set, it's still the same data set. Now if I want w1 in this direction, now what I'm saying is that, so this w1 has this line as, let's say, set of all x such that w1 transpose x equals 5. This was our earlier w. Now this w1 I will not allow in my set of feasible w's. I'm only going to allow w such that the gamma is exactly 1. Now I can always get a W such that gamma is exactly 1, right? So if I find a direction which separates my data set positives from the negatives correctly, then I know that I can scale my W1 to make sure that my gamma is always 1. For example, in this case, I can always set W1 divided by 5 transpose X is equal to 1. This is also the equation of the line set of all X such that W1 by 5 transpose X equals 1. Now I can say that this is my W1 prime, which satisfies W1 prime transpose X equals 1, right? So in other words, I now have to scale down this W to this point, right? So in this direction, well, this would be W1 dash. And now with respect to this W1 dash, the same line will have gamma is 1. Right? So which means that the moment I find a direction which separates my positives from the negatives, now I can scale the direction correspondingly such that these lines, which I mean, on which the data, I can push my data, I mean, I can push the lines parallel to this the line passing through origin as much as possible such that it fits the data points on either side. I can always scale my W such that these lines satisfy the equation that W transpose X equals 1 and on the other side W transpose X equals minus 1. Now, because I can do this, now I don't have to worry about gamma. I can simply say that I'll always set gamma to be 1. I'm only going to be searching for W's such that such a W will give me lines which are parallel to the line passing through origin, but then with gamma equals 1. Now, if the moment I've grounded gamma, now it becomes a question of what am I trying to maximize? Earlier I was trying to maximize gamma. Now, because I'm saying that I'm only going to search for W's such that gamma is 1, now what am I trying to maximize, right? So I now have to maximize this, this width, because that's what I'm trying to, make it as large as possible. Earlier we were saying that, well, that width, when you fix W as 1, the length of W as 1, well, that width was just gamma is what we were maximizing. Now the gamma is 1, so this width somehow has to depend on the length. We'll see what that is in a minute. But just to complete this argument, right? So the same thing with respect to W2, right? So we know, let's say if we start with W2 here, that would give me the, light blue separator. This would become my separating. These would become my separating lines. Now this line, if this had X set of all X such that W2 transpose X equal to 3, now then I have to scale this by a factor of 3 to get W2 dash, right? So this would be W2 divided by 3 transpose X equals 1. It's the same line, but then the equation is different for a different W. Now as you can see, right, so if I have a smaller width, then what I'm essentially doing is I'm kind of scaling it by lesser, right? So I started with W1 and W2 with length 1, and then I scaled it correspondingly to make sure that these parallel lines have length have gamma equals 1. Now the amount I should scale will depend on how wide is the separation. Essentially, basically it depends on gamma. So basically now this will give me a different width. The blue line will give me a different width. The red line will give me a different width. Now what we can then say is that we can say our modified formulation as follows. We can say that we want to maximize only over W. The width that W gives with respect to my data set, such that W transpose Xi into Yi is greater than or equal to 1 for all I. This is an equivalent formulation, is what I'm trying to say, right? So now, as you can notice, there is no gamma. The gamma has gone out of this formulation because we are grounding gamma. But you can also notice that I'm not restricting the length of W. What this is saying is that I'm going to allow any W which linearly separates my data set with a margin exactly equal to 1, right? So with this gamma equals 1. But now what I'm going to maximize is this width, right? So this width is the length between these two parallel lines. We have to find what that width is. But then what I'm saying is that once we have find that width as a function of W, then all we have to do is that we have to maximize
Hello.
this width, right? So this is an equivalent formulation, just that we need to now say what is this, what does this width of W mean? The moment we have pin down what is the formula for the width of W, then we have a clean formulation. So let's go ahead and try to find out what is the width of W in this case. Now how can we find the width of W? So what is width of W? Well, what is the width of W? Well, what are we trying to find out? So we have some W, I give you some W, and I say that, well, this W divides, it classifies my data set such that this is the line where W transpose X equals 1, and this is the line where W transpose X equals minus 1. And now I'm asking, what is this width, the length between these two parallel lines? How can we find the length between these two parallel lines? Well, you can simply take any point on one of these lines and then ask the question, well, what is the closest point on the other side, right? So for this point, this would be the closest point, and then the distance between these two closest points is in fact the length between these parallel lines, and this should be independent of which point I take. If I take this point, the closest point on the other line would be this point, and the length would be the same because these are parallel lines. So I can actually set up a problem as follows, right? So I will want to find out, minimize over some z, let's say the norm, the distance between x and z squared, such that let's call this x, this would be our z, such that W transpose X equals minus 1. That is, you start, W transpose Z equals minus 1. You start with a Z which has the property that, so you start with an X which has the property that W transpose X equal to minus 1, right? So X satisfies W transpose X equal to minus 1, right? So this is a property of X. You are looking for Z such that the distance between X and Z is as small as possible, such that W transpose Z equals plus 1. Right, so you want to find the Z on the line W transpose this line, right? So this line, such that W transpose Z equals plus 1, and the distance from X to Z should be as small as possible. But what should X satisfy? X should satisfy W transpose X equals minus 1, right? So now this is an optimization problem in itself, right? So to find this width, now we can try to solve this optimization problem. I won't really bother solving this exactly, but you can again solve this using something called as the method of Lagrange multipliers. If you're aware of it, you can try it out. We won't do that here in detail. But what you will essentially get is that, I can either solve this or I can do half of this. That doesn't matter, because whichever, I can either minimize the distance squared, or half of the distance squared, doesn't really matter. The exact point is going to be the same. The solution to this problem though will turn out to be the width of W will be 2 divided by norm W squared. When I say width of W, I am considering this quantity, right? So the half of the distance squared between these 2 points, right? So that's what I'm trying to minimize, and that quantity happens to be 2 over norm W squared. So this is basically the solution to this problem. Now, as you can see, as a sanity check, the first thing that you observe is that this value depends only on W, and it does not depend on the exact X point that I care about. Only on to considering something called as the method of Lagrange multipliers. If you're aware of it, you can try it out. We won't do that here in detail. But what you will essentially get is that, I can either solve this or I can do half of this. That doesn't matter, because whichever, I can either minimize the distance squared, or half of the distance squared, doesn't really matter. The exact point is going to be the same. The solution to this problem though will turn out to be the width of W will be 2 divided by norm W squared. When I say width of W, I am considering this quantity, right? So the half of the distance squared between these 2 points, right? So that's what I'm trying to minimize, and that quantity happens to be 2 over norm W squared. So this is basically the solution to this problem. Now, as you can see, as a sanity check, the first thing that you observe is that this value depends only on W, and it does not depend on the exact X point that I care about, right? So because this is just a distance between 2 parallel lines, right? So the distance between parallel lines should only depend on what decides the parallel lines, and the only thing that decides the parallel lines is W, not this X, right? So no matter where I took the X, right? So if I take an X here, this would be my Z. If I take an X here, this would be my Z. If my value between the distance between this X and Z cannot naturally depend on X or Z, right? So it only has to depend on W, and as sanity check, we observe that this width is in fact 2 over norm W squared. So which is good, because now we can actually write down the entire formulation that we want, which can be written as follows, right? So what we want to do now is maximize over W, width of W, which is 2 over norm W squared, such that W transpose Xi into Yi is greater than or equal to 1. So this is our modified formulation now. Now this is basically telling us that, then if you go back to our previous picture, it is basically telling us that, if you have a large separator, right? So separator is large, then the corresponding W will have smaller length, right? So why is that? Because the width is inversely proportional to the length squared of W, and that is in fact, if you pause and think about this for a second, you will realize why that has to be true, right? So because if I take a W, if it so turns out that a W that with respect to a data set, a W that gives me the equation of this line as W transpose X equal to 1, and this as W transpose X equal to minus 1, versus the same for the same data set, if I have a different W which gave me a very small width. Now this guy is W2 transpose X equals 1 set of all X for a W2, right? Now because the difference is small, right? So what should happen, right? So now we can ask the question, how should the length corresponding to the W that induced this should be, right? Because this line has to have the equation that W2 transpose X equals 1. Now what essentially we are saying is that the length should be inversely proportional to the width, which means that if this width is small, well, why is this width small? Because the length of the W that produced this is actually large. Why is the length of the W that produced it large? Well, because we are grounding gamma to be 1, right? So on both sides, gamma, for both this equation and this equation, the gamma is now grounded to be 1. So which means that you want, set of all x such that W2 transpose x equals 1. If the width is small, if I told you that the width is small, then the length of x, should be, so the set of all x that satisfies this are all here, right? So these guys, the length of these guys are going to be smaller, right? So because they have to, make this value as 1, right? So which means that if the width is small, then the length of x's are smaller when compared to the x that you would get in the same direction for the one which are with a larger width. If the length of x is small, but then the right hand side is 1, then the only way you can make the right hand side 1 is if you make the length of w itself large, right? So here x in any fixed direction, the length of x is small because the width is small, and so to compensate for the smaller x, your w should have longer length, right? So and so w2 will have a longer length than w. So basically, then what we are essentially asking now is that if you want to maximize the width with respect to a particular direction which linearly separates the data, then it is equivalent to minimizing the length or length squared of that particular w. So, and that is also true. You can just look at this equation and argue why that is true, because you want to maximize 2 divided by norm w squared, which is equivalently, you can say that you want to minimize over w half norm w squared such that w transpose xi into yi is greater than or equal to 1. Right? So you can either pose this as a maximization problem where you're trying to maximize the width, or you can pose this as a minimization problem where you're trying to minimize the length of w, because the length of w is exactly equivalent to the minimizing the length of w, length squared of w is equivalent to maximizing the width that w gives you with respect to the data set. Okay, so basically what we have now done so far is the following, just to summarize, right? So we wanted to find a w such that the w separates our data sets with as high a margin as possible. Now what we are essentially saying is that, well, it is equivalent to finding a w with as small a length as possible such that w transpose xi yi is greater than or equal to 1 for all I, right? So for all I, right? So this is our first formulation that we have, right? Now, if you solve this problem, so now the question is, okay, so we've set up the problem, right? So all this that we have discussed so far is to figure out, what is the problem that we want to solve, and we have arrived at the conclusion that this is the problem that we want to solve. Now, the w that comes out of it will have the property that it will separate our data set with, as large a width as possible. Now, if such a w exists, right? So because if your data set is not linearly separable, then no w will satisfy the constraints that we have put down. So this algorithm will just say that, well, there is no feasible solution. But if there is a feasible solution, then you will in fact find such a w with the largest possible width, right? So so this is the problem that we want to solve, right? So now we can solve it in different ways. For instance, you can use gradient-based approaches, what are called as projected gradient descent-based methods, for instance, to solve this problem and so on. We won't really worry so much about the exact algorithm at this point to solve this problem, but what we would be interested in is to understand what insights can we derive from this problem, right? So right now we have a clean optimization objective constraint optimization problem that we want to solve. Now what we want to do is understand any other insights that we can draw from this optimization problem. And typically, when you're solving an optimization problem, one way to derive reasonable insights about the problem itself is to derive what is called as a dual problem to the original problem, the primal problem that you would want to solve, which is just another way of looking at the same optimization problem. But typically, that if you look at it in a different way, you might gain some more insights about what is going on, and that might lead us to more stronger algorithms. So what we are going to do now is to say that, well, here is a problem, here is an optimization problem which you can solve, and then you will get a w which maximizes the width, and we can be happy with that. But then this is only going to solve a problem which is linearly separable. So it is not clear how to adapt this problem when the data is not linearly separable, or if the data has maybe a quadratic decision boundary and things like that. So what we are going to ask ourselves is that, can we look at the same problem in a slightly different way and see if that is providing us some more context about this problem. And what we are going to do next is exactly that. We are going to start with this problem and then convert this into a different problem, equivalent different problem, which will provide us very strong insights about the algorithm, about the formulation itself, right? So that will be called as the dual problem to this problem, which is what we'll start looking at next.
During my prep year, I was in complete isolation from friends and somewhat from family itself.
So we are looking at supervised learning, and specifically we are looking at binary classification. And we started looking at an algorithm which tried to maximize the margin given a set of data points and find a linear classifier. Right. So specifically, we came up with the following formulation. Where given a set of data points, we wanted to find a W in the dimension such that the length of W is as small as possible, such that the W is actually classifying the set of data points with margin 1. Now, we argued that the length being small is equivalent to being the width produced by the parallel lines that correspond to margin equals 1 is large. Right? So, and so you are naturally looking for classifiers or lines which have a smaller length. Now, we said that, well, we can solve this problem using different gradient-based techniques, and that might give us some solution. But what we want to do is to look at the same problem in a slightly different way so that we understand this in a differently, so that it will help us derive what is called as a dual problem for this problem, from which we can derive more insights into the understanding of insights into the problem itself, and further our understanding, and probably try to improve the algorithm, so to say. So for this, we are going to do a small detour to understand this concept in more generality, and then we will talk about specifically what it applies to this problem. So let's call this problem A for the moment. We'll come back to this problem in a minute. For now, what we're going to look at is, you want to minimize some function f of w such that g of w is less than or equal to 0. Note that the problem that we have is of this form, it applies to this problem. So let's call this problem A, and further our understanding, and probably try to improve this algorithm, so to say. So for this, we are going to do a small detour to understand this concept in more generality, and then we will talk about specifically what it applies to this problem. So let's call this problem A for the moment. We'll come back to this problem in a minute. For now, what we're going to look at is, you want to minimize some function f of w such that g of w is less than or equal to 0. Note that the problem that we have is of this form. So here we have some function f of w. Now g of w is not less than or equal to 0; it's greater than or equal to 1. But then you can change it to into appropriate form such that it is less than or equal to 0. Function f of w. Now g of w is not less than or equal to 0; it's greater than or equal to 1. But then you can change it to into appropriate form such that it is less than or equal to 0. Now again, note that in the problem that we have, there are many constraints. There are n constraints corresponding to n data points that we have. Whereas what we are going to first start looking at is just the case of one constraint, and then we will see how the ideas also translate to the case where you have more constraints. Okay. So now what we're going to do is we want to solve this problem. Right? So minimize f of w such that g of w is less than or equal to 0. We are going to come up with a different way to solve this problem, and we'll see why that way is useful, especially in the case that we are looking at. So the way is to first define what is called as a function, new function L, which is called sometimes the Lagrangian function, which is a function of two variables, w and alpha, and is defined as f of w plus, to first define what is called as a function, new function L, which is called sometimes the Lagrangian function, which is a function of two variables, w and alpha, and is defined as f of w plus alpha g of w, where alpha is some real number, right? So it is basically what you're doing is that the objective function f of w is still intact. Now the constraint function becomes part of the objective itself, right? So it is f of w plus some alpha times g of w. Now, why do we care about this function? How is this function even related to the original function? Well, let's try to understand that. So now fix any w. Let's say I give you a w, right? So you fix this w, and I ask the original w. Now, why do we care about this function? How is this function even related to the original function? Well, let's try to understand that. So now fix any w. Let's say I give you a w, right? So you fix this w, and I ask you to consider the following quantity, right? So consider maximum over alpha greater than or equal to 0, L of w comma alpha. That is, consider maximum over alpha greater than or equal to 0, f of w plus alpha g of w. Now I ask you the question, what value can this function take, right? So remember, I gave you a w, maybe w equals 1, 2, 3, 4, right? So that vector. Now I'm asking you to maximize a different quantity with respect to alpha greater than or equal to 0. Now how will this quantity value look like? Well, there are two cases to consider here, right? So now let's look at the first case where g of w is greater than 0. let's say I gave you a w, remember, and that w has some f of w value, some g of w value, right? So it has some objective value. It has now let's look at the first case where g of w is greater than 0. Let's say I gave you a w, remember, and that w has some f of w value, some g of w value, right? So it has some objective value. So now let's look at the first case where g of w is greater than 0. Let's say I gave you a w, remember, and that w has some f of w value, some g of w value, right? So it has some objective value, it has some constraint value also, which are evaluated at f of w and g of w. Now, let's say for the w that I gave you, it so happens that g of w is greater than 0. Maybe g of w is 5, right? So it's a positive quantity, strictly positive quantity. Now, how big can you make this function now? Let's say I give you a w for which f of w, and you are looking at f of w and g of w, you realize f of w is maybe minus 100 and g of w is 5, for example, right? So for the w that I gave you, maybe the w is 1, 2, 3, 4. D is 4-dimensional. This is the w that I give you. Now what I'm asking then is, you want to maximize over alpha greater than 0 minus 100 plus alpha times 5. Now alpha is some positive quantity, or non-negative quantity. I can put any non-negative quantity here, but then I want to push this value, the sum, as high as possible. Now how high can I push this? Well, if you look at this, right, so if I set alpha equals 1, then this value is, for alpha 1, this is minus 95. For alpha equals 10, this is minus 100 plus 10 into 550, which is minus 50. If alpha equal to 100, then this is minus 100 plus 100. If I increase alpha, it looks like I can push this value as high as I want, right? So and that is true because I fixed the w. F of w is some fixed number. It can be as small as you want, but then it's a fixed number. It's not going to change as I change alpha to 5, which is 400. 500 minus 100 is 400, and so on. So as I increase alpha, it looks like I can push this value as high as I want, right? So and that is true because I have fixed the w. F of w is some fixed number. It can be as small as you want, but then it's a fixed number. It's not going to change as I change alpha. On the other hand, this guy is going to change as I change alpha, and because g of w is positive now, and I'm allowed to choose alpha which are greater than or equal to 0, I can make alpha arbitrarily large, and the whole thing goes arbitrarily large positive quantity, which means that I can push this whole quantity to be infinity. Which means if the w that I gave you had the property that g of w is greater than 0, then this function evaluates to infinity. Now we'll see why that's useful in a minute. But now let's also look at the case where g of w is less than or equal to 0. Right. So now here is another case where g of w is less than or equal to 0. Let me put a box here. Separate this. Now in this case, maybe w is maybe you have a different w. W is 3, 4, 5, 6. Now f of w here is minus, let's say f of w is 100 and g of w is minus 5. Now what I'm trying to maximize is, earlier it was minus 100 plus 5 alpha. Now it is 100 minus 5 alpha. Now again, I'm only allowed to have non-negative alpha. Right. So if I set alpha equals 1, this value is 100 minus 5 alpha is 95. If I set alpha equals 10, this value is 50. Right? So the value actually goes down as I increase alpha, right? So because of this negative sign. Of course, I cannot set alpha as negative because I'm only allowed to maximize alpha greater than or equal to 0. So how much can I increase this? Well, I can always set alpha equals 0 to get 100 minus 0, which is 100. Right? Any positive alpha is going to only reduce this quantity. So the maximum value that I can get is actually 100 only, which is f of w. So which means that if g of w is less than or equal to 0, then this function evaluates to, because alpha is greater than or equal to 0. Well, if g of w is strictly less than 0, I will just set alpha as 0 to make this value equal to f of w. If g of w is equal to 0, then doesn't matter what alpha I set, this value is always, second term is always going to be 0, the first term will be f of w. So in both the cases, this term is going to be f of w if g of w is less than or equal to 0. Right? So what then happens is that something interesting has actually happened. Right? So now here is a new function which, if I give you a w, if the w satisfies g of w less than or equal to 0, then this new function evaluates to f of w. If the w does not satisfy g of w less than or equal to 0, that is, it satisfies g of w greater than 0, then this function evaluates to infinity. Now, so to get a feel for this, imagine this picture, right? So maybe this is our space of w, right? So this is w, maybe w is a two-dimensional vector, w1 and w2 are two components, and now here is the space. This is the set of all possible w's for which, let's say, g of w is less than or equal to 0, right? So let's consider the shaded region. Now, what we are saying essentially is that, right? So this is w, maybe w is a two-dimensional vector, w1 and w2 are two components, and now here is the space. This is the set of all possible w's for which, let's say, g of w is less than or equal to 0. Right? So let's consider the shaded region. Now, what we are saying essentially is that, if I give you a w here, right, so w equals w1, w2 here, right, so this is w1, this is w2. If I give you this w, then the function max of alpha greater than or equal to 0, f of w plus alpha g of w evaluates to f of w. Right? So at this point, if I ask the function's value, that value is going to be g of w. At this point, the function's value is at this point the function's value is going to be f of w. Why? Because that's the argument that we made. If g of w is less than or equal to 0, then the function evaluates f of w. So let me also say what the shaded region is. The shaded region is the set of all w such that g of w is less than or equal to 0. Inside this, whenever I give you a point, it will evaluate to the corresponding function f of w. On the other hand, if I give you a w outside this for which g of w is greater than 0, then it will evaluate to infinity. right? So which means that there is a region where the function evaluates to some finite value, which is f of w, and outside this region it kind of goes to infinity. So that's the kind of function this guy is, right? So if you think of this as a function of w, right? So now how can we use this function of w? Well, we can do the following. Now, if I want to find the minimum value, right? So for every w, I know what this function evaluates. So it either evaluates f of w or infinity. Now, if I want to find that w where this function takes the smallest value, right? So I want to minimize over w, maximize over alpha greater than 0, f of w plus alpha g of w. If this is what I care about, then what does this plus w, and outside this region it kind of goes to infinity. So that's the kind of function this guys, right? So if you think of this as a function of w, right? So now how can we use this function of w? Well, we minus 5 alpha is 90. I said alpha. Now again it was 100 into 5, which is 400. 500 minus 2. As cases, this term is going to be f of w is evaluate to infinity, right? So which means that there is a region where the function evaluates to some finite value, which is f of w, and outside this region it kind of goes to infinity. So that's the kind of function this guy is, right? So if you think of this as a function of w, right? So now how can we use this function of w? Well, we can do the following. Now, if I want to find the minimum value, right? So for every w, I know what this function evaluates. So it either evaluates f of w or infinity. Now, if I want to find that w where this function takes the smallest value, right? So I want to minimize over w, maximize over alpha greater than 0, f of w plus alpha g of w. If this is what I care about, then what does this mean? This means that, well, here is the black box, right? So which is this function where if I give a w, it evaluates to f of w if w satisfies g of w equals 0. Now, here is another w, maybe w2, which will evaluate to infinity because g of w2 was greater than 0. Here g of w1 was less than or equal to 0. Now, I am trying to give different values of w as input and see which one gives me the smallest value. Now, there will be some w for which this value will be smallest. And necessarily that w has to be somewhere here, right? So inside this shaded region, that is w star. Why? Because outside this shaded region, this function evaluates to infinity. Inside this shaded region, it evaluates to f of w. And so this w star has the property that among all w's which are in the shaded region, it has the smallest value. But what are the w's which are in the shaded region, which are exactly the w's for which g of w is less than or equal to 0? Which means that if I try to find the minimum over w, maximum over alpha greater than or equal to 0, f of w plus alpha g of w, this is equivalent to finding that w which minimizes f of w in the shaded region where g of w is less than or equal to 0. Now, this was the original problem that we wanted to solve. What we are saying is that you can either solve the original problem or you can solve this min-max problem. Both are equivalent. Right? So these two are exactly the same. These will give you exactly the same answer. That is what we have seen so far, right? So let me note that down. Right. So let's call this B. Now this is a nice equivalence. Basically, you have written a minimization problem, a constrained minimization problem, as a min-max problem. Now the question arises is, when you have a min-max problem, one can ask the question, can we swap min and max in B? This is the first question we'll ask. So basically, in other words, I'm asking if I look for the function, well, of course you can always swap, but the question is, if you swap, then does it affect the final answer, right? So can we swap and not affect the final answer is what you're asking. That is, instead of saying min over w max over alpha greater than or equal to 0 something, can I look at max over alpha greater than or 0, min over w something, the same thing, right? So do these things, are these things the same thing, right? So will they evaluate to the same value? Well, in general, they don't necessarily have to evaluate to the same value. In general, the answer is no. You cannot swap the min and max and hope that they evaluate to the same value. But if f and g are nice functions, right? So are nice functions. Well, by nice I mean in our context convex functions. Then yes, you can in fact swap these two things, right? So then yes. So this is a very fundamental result in convex optimization called convex duality result. We won't prove this result, but those who are interested should look at a convex optimization course or convex optimization book where this result would be proved. If f and g are convex, then this swapping is allowed, right? So which means that what that essentially tells us that then is that, so I can either solve min over w, max over that swapping is allowed, right? So which means that what that essentially tells us that then is that, so I can either solve min over w, max over alpha greater than 0, f of w plus alpha g of w. Either I can solve this problem or I can solve max over alpha greater than 0, min over w, f of w plus alpha g of w. I get the same answer no matter I solve which one, right? Which of either. Right? So, but then this course only
seen what convex functions are, right? So for our purposes, the most important convex functions that we will encounter, at least in this particular algorithm that we've been looking at, or this includes quadratic functions, this includes linear functions. These are all convex functions. So we can very well assume that the statement that I made holds for quadratic function and linear function, and that's all you need for our understanding for this point. Now, again, the original problem that we started looking at just had one constraint, right? So this was the original problem; we just had one constraint, but very similar ideas carry over for multiple constraints also. Let me make a note of that, right? So for multiple constraints, the same kind of ideas hold true, which is, let's say you wanted to solve min over w of w, g2 of w, and so on, sum till gk of w, whatever k this might be. Right? So you have k different constraints, right? So, and you have this problem that you want to solve. Now this is equivalent to solving min over w, now max over. Now, because there are multiple constraints, you will have to have an alpha corresponding to each of these constraints, right? So you will have alpha 1 dot 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 alpha k if there are k constraints. Let me make that number clear. I equals 1 to k. So you have k different alphas, and again the function itself is the same, right? So f of w. But now because there are k different alphas, this will be alpha 1 g1 of w plus alpha 2 g2 of w plus dot 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 plus alpha k gk of w. This will be our modified function. This will be the min max problem that these guys will be equal to. But then you will not allow all alphas. You have to make sure that each of these alphas is greater than or equal to 0. Right? So you're only searching the space of alphas greater than or equal to 0. You can do exactly the same argument like how we did. Even if one of these constraints is not satisfied, then you can make this quantity go up to infinity. Whereas if all the constraints are satisfied, then this quantity will exactly evaluate to f of w. The same argument that we did earlier, but then now it holds for multiple constraints. So now again, if f and all the g's are convex, then this is also equivalent to maximizing over g1 of w plus dot 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 plus alpha k gk of w. So this again is convex duality, right? So I just wanted to, because our problem has multiple constraints, we should also see the multiple constraints version of it, right? So now let's map this understanding to our problem and see if it helps us. Right? So at this point, it's not clear why this should help us, right? So because we originally wanted to solve a minimization problem with some constraints, we converted it into a min max, and now we're saying that, well, you can either solve the min max or you can solve the max min. That doesn't, at least in first glance, it does not look like it has made our problem any easy to solve, right? So we need to argue why this might be a useful thing to even look at for our case. So let's try to see what benefit do we get if we do this for our problem. Let's go back to our problem and see what our problem was. Right? So our problem was the following: min over half norm w squared, such that w transpose xi into yi is greater than or equal to 1 for all I equals 1 to n. This was our original problem. First question is, does this min-max swap that we will do later, would it apply to our problem? It would apply, because what kind of a function is this of w? Well, this is a quadratic function of w. Right? So there is a squared term, so this is quadratic in w. And what kind of functions are the constraints of w? Well, these are linear functions. Linear in w. This quadratic in w. So both f and gi's are all convex for our problem, and so we can apply the min-max swap in our case, right? So let's try to do that. But before we do that, we have to bring these guys into standard form, where ga of w is less than or equal to 0. So what is the standard form, right? So this is equivalent to 1 minus w transpose xi into yi is less than or equal to 0 for all I equals 1 to n. This is exactly the same as this, right? So I'm just writing this as in the form. Now this would be my gi of w, which is less than or equal to 0. Good. So what does this tell us now, right? So now this is the original problem I wanted to solve. So now I'll write the Lagrangian of w comma alpha. I'm going to write this as alpha, but then the meaning of this alpha is alpha 1, alpha 2, dot 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 alpha n, because there are n constraints for our case. So each of these constraints will have a corresponding alpha associated with it, and I'm going to think of the whole vector as I'm going to indicate it using alpha, just to declutter notation. So what is the Lagrangian going to look like? Well, I'll first write f of w, which is half norm w squared, plus it's going to be alpha 1 times j of g1 of w plus alpha 2 times g2 of w dot dot dot, which can be written as sum over I equals 1 to n
alpha I gi of w, but gi of w in this case is just 1 minus w transpose xi into yi, this quantity here, right? So this is our Lagrangian. So now what we are saying is that we can either minimize over w, maximize over alpha greater than or equal to 0, and by which I mean this just means alpha 1 greater than or equal to 0 dot 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 alpha n greater than or equal to 0. That's what this means. You want to min max this half norm w squared plus sum over I is 1 to n alpha I 1 minus w transpose xi yi. This is equivalent to max over alpha greater than 0, min over w, the same thing, half norm w squared plus sum over I is 1 to n alpha I 1 minus w transpose xi yi. It's exactly what we did in general for f and g. Now I have applied it to our problem. We still are not sure why this is going to help, but let's see why it's might help. Okay. Now, the reason why this problem on the right hand side might help us is because of the following fact, right? So earlier we had if I give you a w, right? If I fix a w and try to evaluate the max problem, now that is a maximization over alpha greater than or equal to 0, right? So on the other hand, in the right hand side, now if I fix an alpha greater than or equal to 0 and I try to minimization and I try to minimize this over w, now here there are absolutely no constraints on w, right? So for any fixed alpha, now this w's minimization is an unconstrained problem, which means I know how to do unconstrained minimization, right? So what I will do is I'll take the gradient of this function with respect to w, the higher order analog of derivative, and then try to set it to 0 and see what happens. I can do that, right? So let's try that for this particular problem and see what happens, right? So what I'm trying to do is I'm going to try to solve the right hand side problem. To understand the right hand side problem, let's say fix some alpha greater than or equal to 0, arbitrary alpha greater than or equal to 0, and then ask the question, well, maybe
So currently I have reached a point like I am able to understand 30 or 40% of this what is going on, and I am kind of tired. The back started paining and I don't feel much energetic.
if you have 3 data points, maybe alpha is 157, right? So some vector that I'm just fixing, right? So arbitrarily I'm fixing some vector alpha, and then I'm asking what is minimization over w, half norm w squared plus sum over I equal to 1 to n alpha I some vector alpha, and then I'm asking what is minimization over w, half norm w squared plus sum over I equal to 1 to n alpha I 1 minus w transpose xi yi. What is the minimizer? What is this value going to be, right? So can I get a hold on this value? Now, because this is an unconstrained optimization over w, now I can take the derivative of this whole thing, or the gradient of this with respect to w, and try to set it to 0. And so that is where the minimization is going to happen. So what is the gradient of this whole thing is going to be with respect to 0? Well, the gradient will solve the following, right? So half norm w squared gradient is just w. So that is, let me write this as w plus sum over I equals 1 to n. There is an alpha I w transpose minus w transpose xi yi gradient is just minus xi yi with respect to w. Now this is the gradient at any w. At the optimal w, this value is going to be 0. Right? Now this is for any alpha that I've given you, right? So this w star, when I say w star, this is the w star, this is the best for the alpha that I gave you, right? So you pick some alpha, and with respect to that alpha, maybe I can even say this is w star alpha, just to indicate that there is a dependence on alpha here, right? So what is w star alpha then? Well, w star alpha then is going to be just sum over I equals 1 to n alpha I xi y. Now what is this telling us? This is telling us the following, right? So we wanted to solve this max min problem right here. Now the moment I fix an alpha, the w has a functional form that depends on this alpha. And what is this functional form? The functional form is a nice functional form. It just is of the form, the w that is best for the alpha that I give you is just linearly combining my data points with alpha. Right? So it's just sum over I equals 1 to n alpha I xi. But remember what are these guys? Right? So alphas are all greater than or equal to 0. That is some fixed quantity. Yi is plus or minus 1. Xi remember is rd. Right? So which means w star alpha is also going to be some vector in rd. Right? So if I give you alpha, then the best w is the linear combination of your data point xi yi is with alpha. That's what this is saying. Right? So which means that I now have to find that alpha which is kind of which maximizes this quantity with respect to all possible alphas greater than or equal to 0. But what is this quantity? Now here we have maximize over alpha, minimize over w. There are two variables.
Okay, so now it's overflowing my mind, like, so I'm going to take a break.